You are holding enough energy in your fingernail to vaporize a city block. Not in some distant future, not in theory, right now. If the matter in your fingernail met its mirror twin, its antimatter opposite, the explosion would measure 43 kilotons. That is 3 times the bomb dropped on Hiroshima from a fingernail. And yet, when you look around at the universe, at the stars and the galaxies and the endless sprawl of cosmic structure, you see almost no antimatter anywhere, which means something impossible happened. Because when the universe began, the Big Bang should have created matter and antimatter in perfect balance, particle and antiparticle, equal and opposite. And within seconds, they should have found each other, annihilated completely, and left behind nothing but light. No atoms, no stars, no planets, no you. The fact that you exist at all means the universe cheated. Somewhere in the first fractions of a second, a tiny glitch tipped the scales. 1 extra matter particle for every billion pairs. That lone survivor is everything. But no one can tell you what caused it. For decades, physicists have been chasing this asymmetry like detectives hunting a ghost. CERN has trapped antimatter atoms for over 16 minutes, the longest in history, searching for any difference, any clue that explains why we are here. They have measured it, cooled it, held it in magnetic bottles, suspended in perfect vacuum, and the antimatter behaves exactly like matter, which makes the mystery worse. Because if there is no difference, there should be no us. So what broke the balance? What allowed the universe to survive its own birth? And why, after billions of years and thousands of experiments, are we still searching for the answer? Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You exist. That is, statistically speaking, impossible. Not metaphorically impossible. Not philosophically unlikely. Physically, by the rules written into the fundamental architecture of the cosmos, you should not be here. The planet beneath your feet should not exist. The sun should not exist. Every star you've ever seen in the night sky, every galaxy spiraling through the void, every atom in your body, all of it should have been erased from existence roughly 13.8 billion years ago in the largest explosion reality has ever known. And yet here you are, breathing air made of particles that defied their own extinction. Reading these words on a screen built from elements that, by all rights, should have annihilated themselves out of the universe before the first second had even finished ticking. This is not a small problem. This is not some minor footnote in the textbook that physicists politely disagree about over coffee. This is the central mystery at the foundation of everything. The universe is made of matter. It should not be, and nobody on Earth can tell you why. Let's start at the beginning, which is always a useful place to start when the thing you're trying to explain is the survival of all existence. 13.8 billion years ago, give or take a few 100 million years, depending on whose numbers you trust, the universe began. We call it the Big Bang, which is a terrible name for what actually happened because nothing banged and there was no sound, but the name stuck, and now we're stuck with it. In that first fraction of a second, the universe was unimaginably hot and dense. Energy concentrated into a volume smaller than a single atom. And as space expanded and cooled, that energy began to condense into particles. Here's where the trouble starts. According to every law of physics we have ever tested, when energy becomes dense enough, it doesn't just produce matter. It produces matter and antimatter in equal amounts. Always, no exceptions. Every time you create an electron, you also create a positron. Every time you create a quark, you also create an antiquark. Particle and antiparticle, born together, mirror images of each other, identical in every way except for one critical difference. Their charges are opposite. An electron carries a negative charge, a positron carries a positive charge, a proton is positively charged, an antiproton is negatively charged. Same mass, same spin, same quantum properties, just flipped. And here is the part that makes the universe impossible. When a particle meets its antiparticle, they annihilate completely. Both particles vanish, and their entire mass converts directly into energy. Not some of their mass, all of it. Einstein's most famous equation applies here with brutal efficiency. E equals mc squared, mass times the speed of light squared. The speed of light is roughly 300 million meters per second. Square that number and you get 90 trillion. So for every kilogram of matter that meets a kilogram of antimatter, you release 90 trillion joules of energy. That's more energy than a large nuclear power plant generates in an entire day, released instantly from 2 kilograms of material. So here is what should have happened. The Big Bang produces energy. That energy becomes particles. Half of those particles are matter, half are antimatter. The universe is newborn, extremely dense, and everything is packed together in a volume smaller than a grapefruit. Matter and antimatter touch. They annihilate, all of it. Every particle finds its opposite. They embrace, they vanish, and the universe becomes nothing but a bath of radiation expanding into the void. No atoms, no chemistry, no stars, no planets, no complex structures of any kind. Just light, spreading thinner and colder forever. That is what the math predicts. That is what the standard model of particle physics, the most successful theory in the history of science, says should have happened. A perfectly symmetrical universe where matter and antimatter are created equally should destroy itself almost immediately, leaving behind only the faint glow of its own suicide. And yet, here we are. Every atom in your body is made of matter. The chair you are sitting in is matter. The air in your lungs is matter. The earth is matter. The sun is matter. Every star in the Milky Way, every galaxy in the observable universe, all matter. We have looked very carefully with very good telescopes. We have searched for signs of antimatter galaxies, regions of space where antimatter clumped together the way normal matter did. If such places existed, we would see the telltale signature of annihilation radiation at the boundaries where matter and antimatter regions met. We see nothing, no large-scale antimatter structures anywhere. The universe, as far as we can tell, is made almost entirely of matter. Almost entirely. Not completely. That word almost is doing an enormous amount of work in that sentence, because the fact that it is almost and not entirely is the only reason anything exists. Somewhere in the first moments after the Big Bang, something happened. Some process, some asymmetry, some tiny deviation from perfect balance tipped the scales. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. One extra particle in 1,000,000,000. That is the margin. That is the razor's edge. 1,000,000,000 matter particles met 1,000,000,000 antimatter particles and annihilated into radiation. One matter particle was left over. And that leftover particle, multiplied across the entire volume of the early universe, became everything. You are made of leftovers. So is everyone you have ever met. So is the ground beneath your feet and the sky above your head. The entire visible universe is the debris of an asymmetry so slight, that if you had been standing in the early cosmos with a cosmic scale and tried to measure the imbalance, you would have needed to count to 1 billion just to find one extra particle on the matter side of the ledger. And yet, that 1 in a billion excess was enough. It survived the annihilation, it cooled, it clumped, it formed hydrogen, then stars, then galaxies, then planets, then eventually you, sitting here 14 billion years later, trying to figure out how any of this happened. The Standard Model does not explain this at all. The Standard Model is extraordinarily good at predicting what particles exist, how they interact, and what happens when you smash them together at high speeds. It has been tested in thousands of experiments over the past 50 years, and it passes every test with flying colors. But when you ask it why there is more matter than antimatter, it shrugs. The mechanisms that could generate such an asymmetry within the Standard Model are far too weak. They predict an imbalance of maybe 1 part in 10 billion, not 1 part in a billion, off by a factor of 10. In physics, being off by a factor of 10 is not a rounding error. It is a sign that something fundamental is missing. This is what physicists call the baryon asymmetry problem. Baryons are particles made of 3 quarks. Protons and neutrons are baryons. Most of the mass in your body comes from baryons. The problem is that baryons should not be here in any significant number. They should have annihilated with antibaryons, leaving behind only radiation. The fact that they did not means one of 2 things. Either the laws of physics are not perfectly symmetric between matter and antimatter, which would be strange because every experiment we have ever done suggests they should be, or something happened in the very early universe that we do not understand, some event or process that operated outside the rules we currently know. Both possibilities are uncomfortable. The first possibility means our understanding of symmetry, one of the most beautiful and powerful concepts in all of physics, is incomplete. Symmetry is supposed to be fundamental. The laws of physics should not care whether you are made of matter or antimatter. They should treat both identically. If they do not, then somewhere buried in the equations is a bias, a preference, a thumb on the scale, and we would need to find it. The second possibility is worse. If something happened in the early universe that broke the balance, something that operated under conditions we cannot recreate in any laboratory on Earth, then we might never fully understand it. We can theorize, we can build models, we can run computer simulations, but we cannot rewind the universe and watch what actually happened in those first fractions of a second. The evidence has been erased, diluted by 14 billion years of expansion and cooling. All we have are the consequences. A universe made of matter and a gaping hole in our theory where the explanation should be. Andrei Sakharov, the Soviet physicist who later became a human rights activist and spent years under house arrest for criticizing his own government, was the first person to outline what conditions would be necessary to generate a matter-antimatter asymmetry. In 1967, he published a paper listing 3 requirements. First, there must be processes that violate baryon number conservation, meaning reactions that can create more baryons than antibaryons. Second, there must be a violation of what physicists call C-symmetry and CP-symmetry, which are fancy ways of saying the laws of physics must treat matter and antimatter slightly differently. Third, these processes must occur out of thermal equilibrium, meaning the universe must be cooling and expanding fast enough that particles cannot simply annihilate back into balance. All 3 conditions, Sakharov argued, must be met. Miss even one, and the universe resets to symmetry. Matter and antimatter annihilate in equal numbers, and you are left with nothing. The remarkable thing about Sakharov's conditions is that they are not impossible. the standard model contains processes that violate CP symmetry. We have observed them in particle accelerators, but as I said earlier, those violations are weak, too weak. They cannot account for the matter-antimatter imbalance we actually observe, which means either there are additional sources of CP violation we have not yet discovered, or the conditions in the early universe were far stranger than we currently assume. Some physicists have suggested that the asymmetry was not generated during the Big Bang at all, but was instead built into the initial conditions of the universe. Maybe the universe simply started with more matter than antimatter, for reasons we will never know. This explanation is deeply unsatisfying because it does not explain anything. It just moves the mystery backward one step and says, "It was like that from the beginning, do not ask why." Science is supposed to ask why. That is the entire point. Shrugging and calling something an initial condition is giving up. Others have pointed to more exotic possibilities. Maybe the asymmetry comes from physics operating at energy scales far beyond anything we can reach in a laboratory. Grand unified theories, which attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework, predict particles and interactions that could generate the necessary imbalance. But those theories operate at energies trillions of times higher than what the Large Hadron Collider can achieve. We cannot test them directly. We can only look for indirect evidence, subtle imprints left behind in the cosmic microwave background, or in the behavior of neutrinos, or in the decay rates of particles we can create. There is also the possibility, and this one keeps some physicists awake at night, that the universe is not actually matter-dominated everywhere. Maybe there are regions of space far beyond the observable horizon where antimatter won, where galaxies made of antimatter exist, separated from us by such vast distances that their light has not yet had time to reach Earth. In that scenario, the Big Bang did produce equal amounts of matter and antimatter. They just separated somehow, clumped into different regions, and never met. Our corner of the universe ended up matter-dominated by chance. Somewhere else, unimaginably far away, there could be antimatter planets orbiting antimatter stars, with antimatter astronomers looking up at their antimatter sky, wondering why their universe is made entirely of antimatter. This idea is appealing because it preserves symmetry on the largest possible scale. The universe as a whole is balanced. We just happen to live in a matter-rich bubble. But the idea has problems. Big ones. If matter and antimatter regions exist, there should be boundaries between them. And at those boundaries, annihilation would occur on a cosmic scale. We should see the radiation from those annihilations, a diffuse glow of gamma rays spread across the sky. We do not see it. The gamma ray background we observe is smooth and can be explained entirely by known astrophysical sources like supernovae and black holes. There is no sign of large-scale matter-antimatter annihilation happening anywhere in the observable universe. So we are left with the simplest and most troubling explanation. The universe we can see is matter-dominated because something in the first moments after the Big Bang created a tiny excess of matter over antimatter. That excess survived, everything else annihilated. And now, 14 billion years later, we are trying to reverse engineer what happened based on the faintest clues left behind in particle physics experiments and cosmological observations. The stakes here are not abstract. This is not a puzzle that only matters to theoretical physicists writing papers no one reads. This is the existence problem. If the matter-antimatter asymmetry had not occurred, nothing would exist. No stars to forge heavy elements, no planets to host chemistry, no chemistry to build life. The fact that you are here reading this, the fact that anything is here at all, depends entirely on a process we do not understand, operating under conditions we cannot recreate, producing an imbalance we cannot fully explain. And here is the part that makes it worse. We know antimatter exists. We can make it. Particle accelerators produce antimatter every day. CERN, the European Organization for Nuclear Research, has been creating and studying antimatter for decades. They have built machines capable of trapping individual antiprotons and positrons, holding them suspended in magnetic fields so they do not touch normal matter and annihilate. They have even created antihydrogen, the antimatter version of the simplest atom in the universe, and kept it stable long enough to study its properties. Every test we have done shows that antimatter behaves exactly like matter, just with opposite charge. Drop an antihydrogen atom in a gravitational field and it falls down, not up. Shine light on it, and it absorbs and emits photons at the same wavelengths as normal hydrogen. There is no hidden difference, no strange property that would explain why matter won and antimatter lost. The two are mirror images, identical in every measurable way, except for the one fact that the universe chose one over the other. That choice, that tiny bias, that 1 in a billion excess, is the reason anything exists, and we do not know why it happened. The entire mass of your body, converted directly into pure energy, would be enough to power the United States for about a week. Every atom, every molecule, every cell, all of it transformed into light and heat according to the most famous equation in physics, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is roughly 300 million meters per second. Square that number and you get 90 trillion. Multiply your body's mass by 90 trillion and you get a number so large that it stops meaning anything to human intuition. We do not have the machinery to make that conversion happen. Our bodies are stable. The atoms that make us up are locked together by forces that do not simply let go. But there is one reaction in nature that achieves total conversion. One process where mass does not just partially transform into energy the way it does in a nuclear reactor or a hydrogen bomb. One reaction where 100% of the matter involved disappears and becomes radiation. Matter meets antimatter. They touch, they annihilate. And every gram of mass on both sides converts into 180 trillion joules of energy. Let's be specific, because the numbers here matter, and they matter in a way that should make you uncomfortable. Take 1 gram of antimatter, about the mass of a paperclip. Now bring it into contact with 1 gram of normal matter, another paperclip's worth. The moment they touch, both masses vanish. What you get in return is an explosion equivalent to 43 kilotons of TNT, not 43 tons. 43,000 tons. That is roughly 3 times the yield of the atomic bomb dropped on Hiroshima in 1945. 3 Hiroshimas from 2 grams of material, 1 from matter, 1 from antimatter. Together they weigh less than a nickel. The Hiroshima bomb, little boy, carried about 64 kilograms of uranium. Of that 64 kilograms, only about 1 kilogram actually underwent fission. And of that 1 kilogram, only a tiny fraction, less than 1%, converted into energy. The rest of the mass remained as fission fragments, radioactive debris scattered across the city. The explosion that killed an estimated 80,000 people instantly, and tens of thousands more in the months that followed, came from less than a gram of matter converting into energy. Less than a gram out of 64 kilograms. The efficiency was abysmal, and it was still enough to erase a city. Now imagine the same yield from 2 grams total. No uranium core, No plutonium trigger, no complex implosion mechanism, just two paper clips, one matter, one antimatter. Touch them together and you get 43 kilotons. The difference is not subtle, it is not incremental. It is a completely different category of power. Nuclear fission, the reaction that powers every atomic bomb and every nuclear reactor currently operating on Earth, converts about 0.1% of mass into energy. The rest stays behind as lighter elements, still matter, still mass, just rearranged. Nuclear fusion, the reaction that powers the sun and hydrogen bombs, does better. It converts about 0.7% of mass into energy. Antimatter annihilation converts 100%. Every single atom of mass on both sides becomes energy. There is no waste, there is no leftover material. There is only light, gamma rays, neutrinos, and a spray of high-energy particles moving outward at speeds close to light itself. This is what Einstein's equation actually means when you take it seriously. Mass and energy are not separate things. They are the same thing in different forms. Matter is frozen energy. Antimatter is frozen energy with opposite charge. When the two meet, the freeze breaks and the energy is released all at once in the most efficient reaction physics allows. You cannot do better than 100% conversion. Annihilation is the ceiling. To put that in perspective, gasoline releases about 47 million joules per kilogram when burned. That sounds like a lot until you realize that annihilating 1 kilogram of matter and antimatter together releases 90 quadrillion joules. 90,000 trillion. That is roughly 2 billion times more energy than gasoline per unit mass. A single kilogram of antimatter reacting with a kilogram of matter releases the same energy as 21 megatons of TNT. The largest nuclear weapon ever detonated, the Soviet Tsar bomber in 1961, had a yield of 50 megatons. You could match almost half of that with 2 kilograms of material, one matter, one antimatter, fitting comfortably in the palm of your hand. The Tsar bomber weighed 27 metric tons. The explosion was so powerful that the shockwave circled the Earth 3 times. The fireball was visible from 1,000 kilometers away. Windows shattered in Norway and Finland. Seismographs around the world recorded the blast as an earthquake. And that entire event, the most powerful explosion humans have ever created, could be replicated with less than 5 kilograms of matter and antimatter combined. 5 kilograms, the weight of a large house cat. This is not theoretical. The physics is settled. We know exactly how much energy you get from annihilation because we have measured it in particle accelerators thousands of times. When an electron meets a positron, they annihilate into 2 gamma-ray photons. The energy of those photons matches the mass of the particles with perfect precision. Einstein's equation holds every single time. Scale that reaction up from individual particles to grams, and the math does not change. 1 gram of antimatter plus 1 gram of matter equals 43 kilotons. It is not an estimate, it is not a model. It is arithmetic. The comparison to Hiroshima is unavoidable, and it is used constantly in popular explanations of antimatter for a reason. Hiroshima is the benchmark. It is the event that showed the world what 15 kilotons of energy release looks like when concentrated into a fraction of a second. Photographs taken in the hours after the blast show a city flattened in a radius stretching more than 2 kilometers from the epicenter. Buildings reduced to rubble, fires burning across miles of wreckage. The iconic mushroom cloud rose to a height of more than 10 kilometers. That is what 15 kilotons does. Now multiply that by 3. That is what 1 gram of antimatter does. Nagasaki, hit 3 days later with a plutonium bomb called Fat Man. experienced a yield of about 21 kilotons. 43 kilotons is double Nagasaki. 2 paperclips worth of matter and antimatter would produce an explosion twice as powerful as the bomb that destroyed an entire city and killed more than 70,000 people. And you could carry the fuel in your pocket if it were not for the minor inconvenience that touching it to anything made of normal matter would cause it to explode instantly with the force of 3 nuclear weapons. This is why antimatter is not just interesting, it is terrifying. Not because it exists in large quantities, it does not. Not because anyone has figured out how to weaponize it, they have not. But because the energy density is so obscenely high that even tiny amounts you could measure on a kitchen scale, carry destructive potential that exceeds almost everything else in the human arsenal. A milligram of antimatter, 1/1000th of a gram, reacting with a milligram of matter, releases energy equivalent to about 43 tons of TNT, not kilotons, tons. That is still roughly the yield of the largest conventional bombs dropped during World War II. The British Grand Slam bomb, one of the heaviest non-nuclear weapons ever used, weighed 10 tons and carried about 5 tons of explosive. A milligram of antimatter would release 8 times that much energy. A milligram, the weight of a single grain of sand. Scale it down further. A microgram of antimatter, 1/1,000,000th of a gram, annihilating with a microgram of matter, releases energy equivalent to about 43 kilograms of TNT. That is enough to destroy a building. 1/1,000,000th of a gram. You could not see it with the naked eye. It would be invisible. And it would take out a city block. This is not science fiction. This is just math. The equation does not care about your intuition. It does not care that the numbers feel absurd. Mass times the speed of light squared gives you energy, and the speed of light is a very large number. Square it, and it becomes enormous. Multiply even a tiny mass by that enormous number, and the result is explosive in the most literal sense. The practical problem, and this is the only reason antimatter has not already reshaped human civilization or ended it, is that making antimatter is staggeringly difficult and storing it is nearly impossible. Every antimatter particle ever created on Earth was made in a particle accelerator, and the process is breathtakingly inefficient. CERN, which operates the world's most powerful particle accelerators, has been producing antimatter for decades. The efficiency of antiproton production, meaning the ratio of energy you put in to the amount of antimatter you get out, is roughly 1/1000,000th. You pour in 1 billion units of energy and you get 1 unit of antimatter. The rest is lost to heat, radiation, and the inefficiencies of the machinery. To produce 1 gram of antimatter at that efficiency would require about 100 quadrillion joules of energy. That is roughly the total annual energy consumption of the United States, all of it. Every power plant, every car, every light bulb, running for an entire year just to produce 1 gram of antimatter. And that is assuming perfect collection and storage, which does not exist. In practice, the inefficiencies compound. Most of the antimatter produced in accelerators is lost within microseconds. It annihilates against the walls of the containment chamber or drifts into stray atoms of gas before it can be captured. Storage is the other nightmare. Antimatter cannot be kept in a bottle. It cannot sit on a shelf. The instant it touches normal matter, any normal matter, it annihilates. So you need a container that is not made of matter. That container does not exist. What does exist is a workaround, magnetic traps. Devices that use carefully tuned magnetic and electric fields to suspend charged antimatter particles in a vacuum, holding them away from the walls of the chamber so they never touch anything. CERN's antimatter facility can trap a few hundred antiprotons at a time for hours or days. They have managed to trap antihydrogen atoms, which are electrically neutral and much harder to contain, for more than 1,000 seconds. That is a major achievement. It is also nowhere near the kind of bulk storage you would need to accumulate grams of antimatter. A gram of antihydrogen contains roughly 600 billion trillion atoms. CERN has created and trapped a few 100,000 antihydrogen atoms total in the entire history of the program. We are not close. We are not even close to being close. The gap between what we can do now and what would be required to store meaningful amounts of antimatter is measured in factors of trillions. And even if we could store it, even if someone invented a perfect magnetic trap that could hold grams of antimatter indefinitely without power failures or system malfunctions or any of the 1,000 things that go wrong with complex machinery, the danger would not go away. It would get worse. Because now you have a device holding the equivalent of multiple nuclear weapons in a volume the size of a soda can. A power outage and the magnetic field collapses. The antimatter touches the wall, 43 kilotons, instantly. No timer, no trigger, just contact. The hypothetical scenarios write themselves, and they are all nightmare fuel. A teaspoon of antimatter, often cited in popular science explanations as a thought experiment, would hold roughly 5 grams. That is 215 kilotons if it annihilates with an equal mass of matter. 10 times Hiroshima, 15 times Nagasaki. That is the explosive yield you could carry in a spoon if antimatter storage were ever solved, which it will not be anytime soon. But the fact that the physics allows it, the fact that the equation is sitting there waiting, is enough to make the whole idea feel less like science and more like a fuse attached to the foundations of reality. Some researchers have explored whether antimatter could ever be used as fuel. Not for bombs, for propulsion. A rocket engine powered by matter-antimatter annihilation would be the most efficient propulsion system physics allows. You would not need massive fuel tanks. You would not need chemical propellants or nuclear reactors or ion thrusters. You would need a few grams of antimatter and a controlled way to let it annihilate in tiny amounts, using the gamma rays and particles produced to generate thrust. The specific impulse, a measure of rocket efficiency, would be orders of magnitude higher than anything currently available. A spacecraft powered by antimatter could reach a significant fraction of the speed of light. Interstellar travel would shift from science fiction to engineering problem. But there is a reason no one is building antimatter rockets. The production problem has not been solved. The storage problem has not been solved. And even if both were solved tomorrow, the safety problem would remain. You are flying a spacecraft powered by something that, if it escapes containment, annihilates with the force of multiple nuclear weapons. One malfunction and your spaceship does not crash, it explodes. And unlike a chemical rocket explosion, which releases energy stored in molecular bonds, an antimatter explosion releases energy stored in mass itself. There is no comparison. A few grams of antimatter escaping containment would not just destroy the spacecraft. It would vaporize it so completely that no debris would survive. The science fiction writer Arthur the 100th Clarke once said that any sufficiently advanced technology is indistinguishable from magic. Antimatter is the opposite. It is indistinguishable from a weapon. The same properties that make it scientifically fascinating, the perfect mass-to-energy conversion, the staggering energy density, the elegance of annihilation, also make it one of the most dangerous substances that could ever exist in bulk. It is not toxic. It is not radioactive in the traditional sense. It is simply explosive by its very nature. Existence itself becomes unstable around it. And the strangest part of all this, the detail that should bother you more than any of the numbers, is that antimatter is not exotic. It is not alien. It is not a substance that only appears in the cores of distant stars or in the aftermath of supernovae. It is made of the same fundamental particles as normal matter, just flipped. An antiproton is a proton with opposite charge. A positron is an electron with opposite charge. The particles themselves are mundane. The danger comes purely from the fact that we live in a matter-dominated universe. If we lived in an antimatter universe, normal matter would be the dangerous substance. You would store protons and electrons in magnetic traps. You would worry about matter contamination. You would write the same articles explaining how 1 gram of matter plus 1 gram of antimatter equals 43 kilotons. The asymmetry is arbitrary. The danger is not. And that danger scales linearly with mass. 1 gram is 43 kilotons. 10 grams is 430 kilotons. 1 kilogram is 21 megatons. There is no plateau. There is no point where adding more antimatter stops making the explosion bigger. Every additional particle of antimatter is another particle that will annihilate and release its full mass energy equivalent. The math does not saturate. It just keeps going. This is what makes the research at places like CERN so critical and so delicate. They are not just studying antimatter because it is interesting, although it is. They are studying it because it represents the outer edge of what matter and energy can do, the absolute limit of energy density. The point where physics stops being about chemistry and nuclear forces and becomes purely about Einstein's equation written in gamma rays. And they are doing it with machines that can produce and trap individual particles, holding them for seconds or minutes before they drift into a wall and vanish. The people working on these experiments are not careless. They know exactly what they are holding. They know that even the tiny amounts they produce, measured in billionths of a gram, contain more energy per unit mass than anything else in their laboratories. They know that scaling up is not just an engineering challenge, it is a containment problem that might not have a solution. And they know that every measurement they take, every test they run, every property they observe, brings us one step closer to understanding why the universe is made of matter and not antimatter. Why the annihilation happened once, 14 billion years ago, and left behind just enough matter for stars and planets and eventually us. Because that is the real question lurking beneath all of this. Antimatter is not just a curiosity, it is a clue. The fact that it exists, the fact that it behaves exactly like matter except for its charge, the fact that it annihilates so completely when the two meet, all of that tells us something about the rules written into reality. And the fact that it barely exists anymore, that the universe is almost entirely matter, tells us that those rules were not perfectly balanced. Something tipped the scale. One particle in a billion survived, and now we are trying to reproduce that survivor in tiny amounts, trap it, study it, and figure out what it can teach us about the moment everything began. The people trying to trap antimatter are not operating on the scale of grams or even milligrams. They are working with individual atoms, one at a time, holding them for seconds, then minutes, then hours if they are lucky. And every single atom they manage to trap represents a victory against physics that wants very badly to make those atoms disappear. CERN, the European Organization for Nuclear Research, sits on the border between France and Switzerland, just outside Geneva. It is home to the Large Hadron Collider, the most powerful particle accelerator ever built, a ring 27 kilometers in circumference, buried 100 meters underground. The LHC is famous for discovering the Higgs boson in 2012. It smashes protons together at energies high enough to recreate conditions that have not existed in the universe since fractions of a second after the Big Bang. And while the LHC gets most of the headlines, the real antimatter work at CERN happens somewhere else entirely. In a much quieter, much slower, much more delicate set of machines that do not smash anything. They catch things and they hold on. The Large Hadron Collider does produce antimatter. Every time two protons collide at near light speed inside its detectors, the energy of the collision converts into a spray of particles. Some of those particles are antimatter. Positrons, antiprotons, even heavier antimatter particles that only exist for microseconds before decaying into lighter fragments. But those particles are moving far too fast to be useful. They are created at energies measured in billions of electron volts, traveling at speeds so close to the speed of light that they cross the width of the detector in a few billionths of a second before slamming into something and annihilating. You cannot study antimatter at those speeds. You cannot trap it. You cannot hold it still long enough to ask it questions. So CERN built something else, the Antimatter Factory. It is not a factory in any traditional sense. There are no assembly lines, no conveyor belts, no workers in hard hats standing around machinery. It is a collection of interconnected accelerators and decelerators, machines designed to take high-energy antiprotons produced in particle collisions and slow them down, way down. From speeds approaching light speed to speeds slow enough that the antiprotons can be captured in magnetic traps and held in place. The process is absurdly difficult, and the numbers reflect that. CERN's Antimatter Factory produces about 400 million antiprotons per hour. That sounds like a lot. It is not. 400 million antiprotons weigh roughly 6 times 10 to the minus 19 kilograms. That is 6/10 of a billionth of a billionth of a kilogram. You would need to run the facility continuously for more than 50 million years to produce a single gram. And of those 400 million antiprotons produced every hour, the experiments downstream manage to capture about 10%. The rest are lost. They drift into the walls of the beam pipe. They collide with stray atoms of residual gas. They annihilate before anyone can catch them. So the actual number of antiprotons available for trapping at any given time is closer to 40 million per hour. Still a large number by particle physics standards, still nowhere near bulk quantities. Once you have antiprotons, the next step is to make antihydrogen. Hydrogen is the simplest atom in the universe. One proton, one electron. Antihydrogen is the same structure flipped. One antiproton, one positron. The antiproton provides the positive charge in normal hydrogen, but here it is negative. The positron orbits it the way an electron orbits a proton. Same forces, same distances, same quantum mechanics, just opposite charges. If the standard model is correct, and it has been correct about everything else so far, antihydrogen should behave exactly like hydrogen. Same energy levels, same spectral lines, same response to light and gravity. Testing that prediction is one of the primary goals of CERN's antimatter program. But you cannot test it if you cannot make the atoms in the first place. And you cannot make the atoms if you cannot get the antiprotons and positrons to meet at low enough energies that they bind together, instead of just flying past each other. This is where the experiments get clever. The Alpha experiment, one of several antimatter projects at CERN, uses a device called a penning trap to hold clouds of antiprotons and positrons in the same region of space. The trap uses a combination of electric and magnetic fields to confine charged particles in a small volume, typically a few centimeters across. The antiprotons are cooled using a technique called electron cooling, where they are mixed with a cloud of cold electrons. The electrons do not annihilate with the antiprotons because they have the same charge. Like charges repel. But the collisions between antiprotons and electrons transfer energy from the heavier antiprotons to the lighter electrons. The electrons carry that energy away and the antiprotons slow down. Once the antiprotons are cold enough, slow enough, the positrons are introduced. And if everything is aligned correctly, if the energies are low enough and the timing is right, an antiproton and a positron will bind together and form an antihydrogen atom. The first time this worked was in 1995 at CERN's low-energy antiproton ring, a facility that no longer exists but was the predecessor to the current antimatter factory. Researchers detected 9 antihydrogen atoms. 9. The atoms existed for about 40 billionths of a second before annihilating. There was no way to trap them, no way to study them. But the fact that they existed at all was proof of concept. You could make antimatter atoms in a laboratory. The next step was making enough of them that you could do something useful with them. By 2002, 2 experiments at CERN, Athena and Atrap, demonstrated that antihydrogen could be produced in much larger quantities, thousands of atoms per run instead of a handful. The breakthrough came from better control of the antiproton and positron clouds, better cooling techniques, and better understanding of the conditions required for the particles to bind. But the atoms were still moving too fast to trap. They were cold by particle physics standards, but still traveling at speeds of hundreds of meters per second. At those speeds, an antihydrogen atom crosses the width of the experimental apparatus in a few thousandths of a second and hits the wall. Contact with normal matter equals annihilation. Game over. Trapping antihydrogen is vastly harder than trapping charged particles. A charged particle responds to electric and magnetic fields. You can push it, pull it, hold it in place using carefully tuned field configurations. Antihydrogen is electrically neutral. The positive charge of the antiproton and the negative charge of the positron cancel each other out. From the perspective of an electric field, the atom is invisible. You cannot trap it with electricity. You have to use magnetism, and not just any magnetic field. Antihydrogen is very weakly magnetic. The atom has a tiny magnetic moment, a property that comes from the quantum spin of its constituent particles. That magnetic moment is sensitive to magnetic field gradients. If you create a magnetic field that is stronger in some places than others, the atom will be pushed toward the regions where the field is weaker. This is the principle behind a magnetic bottle. You shape the magnetic field so that it is weakest in the center of the trap and stronger at the edges. Antihydrogen atoms that are cold enough and slow enough will be repelled by the strong fields at the boundaries and held in the weak field region in the middle. They float there, suspended in empty space, not touching anything. The Alpha experiment built exactly this kind of trap. A cylinder about 30 centimeters long and a few centimeters in diameter, surrounded by superconducting electromagnets. The inside of the trap is kept at ultra-high vacuum, the best vacuum CERN has ever achieved in an experiment. The pressure inside the trap is about 5 × 10 to the -19 millibar. For comparison, the vacuum of space near Earth's orbit is about 10 to the -12 millibar. The Alpha trap is 10 million times emptier than the space outside the International Space Station. At that pressure, there are so few atoms of residual gas left that an antihydrogen atom can drift around for hours without hitting anything. In November 2010, the Alpha collaboration announced that they had successfully trapped antihydrogen for the first time. 38 events, 38 individual atoms that survived in the trap long enough to be detected when the magnetic field was turned off and the atoms drifted into the walls and annihilated. The signals were unmistakable. Each annihilation produced a characteristic spray of particles, pions and other fragments that lit up the detectors surrounding the trap. The atoms had been held for about 170 milliseconds, less than 2/10 of a second. It does not sound like much. It was everything. Those 170 milliseconds were the first time in history that antimatter atoms had been held in a controlled environment long enough that researchers could confirm they were still there. The reaction in the physics community was immediate. This was not a theoretical prediction. This was not a simulation. This was antimatter, real antimatter atoms, sitting in a trap at CERN, not moving, not annihilating, just existing. BBC covered it. Scientific American covered it. Physics journals ran editorials. Jeffrey Hangst, the spokesperson for the Alpha experiment, told reporters that the result opened the door to precision studies of antimatter. For the first time, physicists had the tools to ask whether antihydrogen behaved the same way as hydrogen. And if it did not, that would be one of the most important discoveries in the history of science. By June 2011, Alpha announced that they had trapped antihydrogen for more than 16 minutes, 1,000 seconds. The improvement came from better magnetic field design and colder atoms. The colder the atoms, the slower they move, and the less likely they are to have enough energy to escape the trap. 16 minutes might not sound revolutionary, but in the world of antimatter research, it was a different era. Minutes are long enough to perform experiments. You can shine light on the atoms. You can measure how they absorb and emit photons. You can test whether the energy levels inside an antihydrogen atom match the energy levels inside a hydrogen atom to within parts per trillion. Those are the kinds of measurements that test the deepest symmetries in physics. The symmetry in question is called CPT symmetry. C stands for charge conjugation, flipping particles to antiparticles. P stands for parity, flipping space like a mirror image. T stands for time reversal, running physics backward. CPT symmetry is one of the most fundamental principles in quantum field theory. It says that if you take any physical process, flip all the charges, flip all the spatial coordinates, and run time backward, the result should be a valid physical process that obeys the same laws. If CPT symmetry holds, and almost every physicist believes it does, then antimatter should behave exactly like matter. An antihydrogen atom should have the same mass, the same energy levels, the same spectral lines, the same response to gravity as a hydrogen atom. Any difference, no matter how small, would mean CPT symmetry is broken. And if CPT symmetry is broken, the standard model is incomplete. There is new physics hiding in the gap. So CERN's antimatter experiments are not just trapping atoms for the sake of trapping them. They are preparing to run the most precise tests of matter-antimatter symmetry ever attempted. Alpha has already measured the charge of antihydrogen and found it to be neutral to within 1 part in a billion, exactly as expected. They have measured the magnetic moment and found it consistent with predictions. The next major goal is spectroscopy, shining laser light on trapped antihydrogen and measuring the exact frequencies at which the atoms absorb and emit photons. Hydrogen spectroscopy is one of the most precisely measured things in all of physics. The energy difference between the ground state and the first excited state of hydrogen, a transition called the Lyman alpha line, is known to 15 decimal places. If antihydrogen differs from hydrogen in that transition by even 1/1,000,000,000%, alpha will see it. As of now, CERN's current antimatter traps can hold about 1 billion charged antiparticles at a time if they are all the same charge. That sounds like a lot. It is not. 1 billion antiprotons weigh about 10 to the minus 18th kilograms. That is 1/1000th of a kilogram. You could hold all the antimatter ever trapped at CERN in your hand if it were not for the minor issue that it would annihilate your hand instantly. But for precision experiments, you do not need grams. You need atoms you can control, atoms you can cool, atoms you can hold still long enough to shine a laser on them and see what happens. The technical challenges here are not subtle. Every component of the experiment has to be carefully designed to avoid introducing stray magnetic fields that could disturb the trap. The vacuum has to be maintained at pressures where even a single atom of hydrogen drifting into the trap could ruin an entire run. The superconducting magnets have to stay cold, which means liquid helium, which means cryogenics, which means another layer of complexity. And the detectors have to be sensitive enough to catch the faint signals of individual antihydrogen atoms annihilating against the trap walls while ignoring all the background noise from cosmic rays, radioactive decay, and electronic interference. The people doing this work are not careless. They know they are holding the most reactive substance in the known universe. They know that the magnetic traps are the only thing keeping their experiments from turning into small explosions. And they know that the amounts they are working with are so small that even if every safety system failed simultaneously and all the antimatter annihilated at once, the energy release would be less than a firecracker. But the principle remains. Antimatter in contact with matter annihilates, always. No exceptions. The traps work because the antimatter never touches anything. The moment the magnetic field turns off, the atoms drift outward, hit the walls, and disappear in a flash of gamma rays. One of the strangest aspects of CERN's antimatter program is how transportable it has become. In November 2025, the base step experiment successfully loaded trapped antiprotons onto a truck and transported them to another facility. Antimatter on a truck. Driving down public roads, the antiprotons were held in a portable penning trap, powered by batteries and surrounded by layers of shielding and vacuum equipment. The entire apparatus weighed about 700 kilograms. Inside, a few million antiprotons floated in a magnetic bottle, isolated from the normal matter universe by electromagnetic fields and the best vacuum technology humans have ever built. The transport was successful. The antiprotons survived the trip. And the experiment demonstrated that antimatter research is no longer confined to the facilities where the antimatter is produced. You can move it, carefully, very carefully, but you can move it. The long-term vision for CERN's antimatter program extends far beyond trapping and spectroscopy. Researchers want to measure how antimatter responds to gravity. Does an antihydrogen atom fall down in Earth's gravitational field the way a hydrogen atom does, or does it fall up? The latter possibility, that antimatter has negative gravitational mass, is considered extremely unlikely by most physicists. It would violate several well-tested principles, including the equivalence principle that underlies general relativity. But unlikely is not the same as impossible, and the only way to know for sure is to measure it. Alpha and other experiments are working on designs for gravity measurements. The idea is to create a cloud of ultra-cold antihydrogen atoms, release them from the magnetic trap, and watch which way they fall before they hit the walls and annihilate. The measurement has to be done in a horizontal orientation to avoid confusion with the much stronger magnetic forces. And it has to be precise enough to detect the tiny acceleration due to gravity, about 10 meters per second squared, in the fraction of a second before the atoms are lost. If antimatter falls up, every textbook in physics gets rewritten. If it falls down, we confirm what we expected and move on to the next test. Either outcome is valuable. But the fact that the question is being asked at all, the fact that we are now at a point where we can even attempt to measure the gravitational behavior of antimatter, reflects how far the technology has come. 20 years ago, the idea of trapping antihydrogen for more than a few microseconds was considered borderline impossible. Today, CERN can create antihydrogen at a rate of about 3,000 atoms per hour and store them for up to 100 hours. That is 4 days. 4 days of an antimatter atom sitting in a magnetic bottle, not touching anything, not annihilating, just existing in a state of perfect isolation from the matter universe around it. The other experiments at CERN's antimatter factory are pursuing parallel goals. The base experiment focuses on measuring the properties of individual antiprotons with extreme precision. They have measured the charge-to-mass ratio of the antiproton to within a few parts per trillion and found it identical to the proton's charge-to-mass ratio within experimental error. They have measured the magnetic moment of the antiproton and found it matches theoretical predictions to within a few parts per billion. Every test so far has confirmed that antimatter behaves exactly as the standard model predicts. No anomalies, no surprises. Just perfect mirror symmetry between matter and antimatter at the level of individual particles. That consistency is reassuring in one sense. It means our understanding of particle physics is solid, but it is also frustrating because it does not explain the big mystery. If matter and antimatter are truly symmetric, why is the universe made of matter? Where did the asymmetry come from? The experiments at CERN cannot answer that question directly because they are studying antimatter in the present day, not in the conditions of the early universe. But they can test whether the symmetry holds in every measurable way, and if they find even one place where it breaks, one property where antihydrogen differs from hydrogen, that would be the first crack, the first hint that the standard model is missing something. And whatever is missing might be the key to understanding why anything exists at all. The work is slow. The results come in pieces. Each measurement takes months or years of preparation. Each trapped atom represents hours of setup time, careful tuning of magnetic fields, precise control of temperatures and pressures and particle densities. And every time the trap is opened, every time the magnetic field is turned off and the antimatter annihilates, the experiment resets. The atoms are gone. You start over. Make new antiprotons. Cool them. Bind them with positrons. Load them into the trap. Repeat. But the progress is real. The trapping times are increasing. The measurements are getting more precise. And the questions being asked are getting deeper. CERN's antimatter program is no longer just about proving that antimatter can be trapped. It is about using trapped antimatter as a tool to probe the foundations of physics, to test whether the universe really is symmetric at the deepest level, to search for the missing piece that explains why we are here instead of nothing. And somewhere in those magnetic bottles, floating in the best vacuum humans have ever created, a few hundred antihydrogen atoms are waiting. Not moving, not decaying, just sitting there, isolated from the matter universe, holding the answers to questions we have been asking since the moment we realized the universe should not exist. The atoms do not know they are important. They do not know they are antimatter. They are just atoms, obeying the same quantum rules as every other atom, and that, more than anything else, is what makes them so valuable. Because if those rules are the same for matter and antimatter, we still do not understand where we came from. And if the rules are different, even slightly, we are about to discover something new. So CERN can trap a few hundred antihydrogen atoms at a time, hold them for hours or days, and run precision tests on them in the best vacuum humans have ever created. That is antimatter made on Earth, controlled, isolated, expensive. The entire antimatter factory produces about 1 nanogram of antimatter over its lifetime, 1/1000th of a gram, spread across decades of operation. And every single particle has to be manufactured from scratch, using particle accelerators that consume enough energy to power a small city. Now here is the part that should bother you. While CERN is carefully trapping individual atoms in magnetic bottles deep underground in Switzerland, antimatter is falling out of the sky, right now, on your head, not one atom at a time, constantly. A steady rain of antiparticles arriving from space at a rate that makes CERN's production look like a rounding error. You are being hit by antimatter particles roughly 100 times per second for every square meter of surface area. Most of them are positrons. Some are antiprotons. A few, very rarely, are heavier antinuclei. And all of them are arriving at speeds close to the speed of light, produced by processes happening thousands or millions or billions of light years away, in some of the most violent environments the universe has to offer. This is cosmic ray antimatter, and it is everywhere. The Earth is soaking in it, always has been. Long before humans figured out how to make antimatter in particle accelerators, nature was delivering it for free. We just did not notice because the particles are invisible, incredibly small, and moving so fast that they pass through the atmosphere and sometimes through your body before annihilating against something solid. But once scientists built detectors sensitive enough to catch them, the signals were unmistakable. Antimatter is not rare in the cosmos. It is common, and the fact that it is arriving here constantly from all directions raises a question nobody has fully answered. Where is it coming from? Cosmic rays are not rays. That is the first thing you need to understand, because the name is a historical accident and it is misleading. Cosmic rays are particles, mostly protons, about 90%. Some are helium nuclei, a few percent. The rest are heavier elements, electrons, and yes, antimatter. They are called rays because when they were first discovered in the early 1900s, scientists did not know what they were. They just knew that something from space was ionizing the atmosphere and producing radiation that could be detected with electroscopes. So they called them rays. By the time we figured out they were particles, the name had stuck. These particles are fast, extremely fast. The most energetic cosmic rays ever detected are traveling at speeds so close to the speed of light that the difference is measured in decimal places you run out of fingers to count. A single cosmic ray proton at the highest observed energies carries as much kinetic energy as a baseball thrown at 60 miles per hour. One proton, moving so fast that relativistic effects compress the entire observable universe into a thin disk from its perspective. If you could ride that proton, the trip from one side of the Milky Way to the other would take a few minutes of your time. From the perspective of the stationary galaxy, the trip takes 100,000 years. That is how fast these particles are moving. Most cosmic rays do not reach those extremes. The typical cosmic ray proton arriving at Earth has an energy of about 1 giga-electron volt, which is roughly the energy of a proton inside CERN's accelerators before it gets boosted to collision speed. Still fast, still moving at a significant fraction of light speed, and still carrying enough energy that when it slams into an atom in Earth's upper atmosphere, the collision produces a cascade of secondary particles. The proton hits a nitrogen or oxygen nucleus. Both particles shatter. Quarks and gluons spray outward. Some of them combine into new particles. Pions, kaons, other short-lived fragments. Those particles decay into lighter particles, muons, electrons, photons, neutrinos, and some of those lighter particles are antimatter. This is secondary antimatter production. It is not antimatter arriving directly from space. It is antimatter created in the atmosphere as a byproduct of high-energy collisions. When a cosmic ray proton with enough energy hits an atmospheric nucleus, the collision can produce pairs of particles and antiparticles, just like the collisions inside CERN's detectors. The energy of the collision converts into mass. Matter and antimatter are created in equal amounts. The matter particles drift down through the atmosphere. The antimatter particles do the same until they hit something and annihilate. Most of them do not make it to the ground. They annihilate in the upper atmosphere within microseconds. But a fraction survive long enough to be detected by instruments on high-altitude balloons or satellites or detectors on mountaintops. And those detections are how we know that antimatter is being constantly manufactured in the sky above us. Secondary antimatter is well understood. The physics is the same physics that happens inside particle accelerators. High-energy collision, particle creation, decay chains, antimatter as one of the products. Nobody is surprised by secondary antimatter. It is expected, predicted, boring as far as antimatter discoveries go. What is not boring is primary antimatter. Antimatter particles arriving from space that were not created in Earth's atmosphere. Antimatter that was created somewhere else, out there, in the galaxy or beyond, and traveled through space to get here. If you can detect primary antimatter and measure its properties, its energy spectrum, its arrival directions, its composition, you can start to figure out where it came from. And that is where things get interesting. The first antimatter particle ever discovered was found in cosmic rays. 1932. Carl Anderson, a physicist at Caltech, was studying cosmic ray tracks in a cloud chamber, a device that makes particle trajectories visible by showing the trails of ionization they leave as they pass through a supersaturated vapor. Anderson saw a track that curved the wrong way, a particle with the same mass as an electron but bending in the opposite direction in a magnetic field. Opposite curvature means opposite charge. Same mass, opposite charge. That is a positron. Anderson did not set out to discover antimatter. He was just looking at cosmic rays, and the antimatter found him. The positron had been predicted 3 years earlier by Paul Dirac, based purely on theoretical grounds, but Anderson's detection was the first experimental confirmation that antiparticles were real, and they were arriving from space. For decades after that, cosmic ray antimatter was a curiosity. Scientists knew it was there. They could detect positrons in cloud chambers and later in more sophisticated detectors. But the rates were low, the measurements were noisy, and nobody had a good explanation for where the primary component was coming from. The secondary production in the atmosphere was obvious. That accounted for most of what was being detected, but there were hints, small excesses in the data, that suggested some of the positrons were coming from space. Not enough to be certain, just enough to be suspicious. Then in 2006, a satellite called Pamela launched. Payload for antimatter-matter exploration and light nuclei astrophysics. The name is a stretch, but the mission was straightforward. Put a detector in space, above the atmosphere, where you do not have to deal with secondary production contaminating your signal, and measure the antimatter content of cosmic rays directly. Pamela could distinguish protons from antiprotons, electrons from positrons, and measure their energies across a wide range. It orbited Earth at an altitude of about 350 to 600 kilometers, well above the bulk of the atmosphere, and it collected data for more than a decade. Pamela found something strange. The positron fraction, the ratio of positrons to electrons in cosmic rays, was higher than expected, not by a huge amount, but enough that it did not match the predictions from models that assumed all the antimatter was secondary. At low energies, below about 10 giga-electron volts, the positron fraction behaved the way the models predicted. It decreased with energy, which makes sense because higher energy cosmic rays are rarer and produce fewer secondary particles per collision. But above 10 giga-electron volts, the positron fraction started increasing. It rose steadily as energy increased, up to the highest energies Pamela could measure, around 300 giga-electron volts. That rising trend was unexpected. It suggested that there was a source of high-energy positrons that the models were not accounting for, a primary source. The obvious candidate was pulsars. Pulsars are rotating neutron stars, the collapsed cores of massive stars that exploded as supernovae. A neutron star is about 20 kilometers across and weighs more than the Sun. The density is so extreme that a teaspoon of neutron star material would weigh about 1 billion tons. When a neutron star rotates, and many of them rotate extremely fast, some spinning hundreds of times per second, the rotation drags the star's magnetic field around with it. Neutron stars have the strongest magnetic fields in the known universe, trillions of times stronger than anything we can produce on Earth. That combination, rapid rotation and insane magnetic field strength, turns the neutron star into a particle accelerator. Here is how it works. The rotating magnetic field rips electrons off the surface of the neutron star and accelerates them to nearly the speed of light. Those electrons curve along the magnetic field lines and radiate energy in the form of gamma rays. The gamma rays are so energetic that they can spontaneously convert into particle-antiparticle pairs, electron-positron pairs. The process is called pair production, and it happens whenever a gamma ray with enough energy passes near a strong electric or magnetic field. The gamma ray vanishes. An electron and a positron appear in its place. The energy of the gamma ray becomes the mass and kinetic energy of the two particles. This is happening continuously in the magnetosphere of a pulsar. Electrons and positrons are being created in enormous numbers, accelerated outward by the magnetic field and ejected into space in a particle wind. Some of those positrons escape the pulsar entirely and travel through the galaxy. They become cosmic rays. If Earth happens to be in the path of one of those positrons, a detector like Pamela or its successor AMS will catch it. And because pulsars produce high-energy positrons preferentially, the energy spectrum should show an excess at high energies, which is exactly what Pamela saw. The rising positron fraction above 10 giga-electron volts matched the kind of signature you would expect from nearby pulsars injecting antimatter into the local cosmic ray population. This explanation has been the leading candidate for more than a decade. It fits the data. It relies on known astrophysical objects. Pulsars are common. There are hundreds of them in the Milky Way within a few thousand light-years of Earth. Some of those are young, energetic, and spinning fast. Geminga and PSR B0656+14, two pulsars relatively nearby by galactic standards, are specifically named in the literature as likely sources. The gamma-ray emission from these pulsars has been observed. Their ages and distances match the diffusion timescales required for positrons to propagate from the pulsar to Earth. The case is strong, not proven, but strong. But pulsars do not explain everything. In 2011, the Alpha Magnetic Spectrometer launched to the International Space Station, AMS-2, a particle detector the size of a small car, weighing more than 7 tons, equipped with a superconducting magnet and layers of tracking detectors designed to measure cosmic rays with unprecedented precision. AMS-2 was built specifically to search for antimatter, to measure the positron fraction, the antiproton fraction, and if it got very lucky, to detect heavier antinuclei like antihelium. The project cost about $2 billion and took more than 15 years to design and build. It is the most expensive and most sensitive antimatter detector ever put in space. AMS-2 confirmed Pamela's results and extended them to higher energies. The positron fraction keeps rising up to about 250 giga-electron volts, then it flattens out or possibly starts to decline. The exact behavior at the highest energies is still being measured because the event rates are low and the statistics are noisy, but the overall trend is clear. There is an excess of high-energy positrons. The excess is real. It is not an instrumental artifact. And the most plausible explanation is still pulsars. But there are problems. One problem is isotropy. The positrons detected by AMS-2 arrive from all directions. There is no preferred direction, no hotspot in the sky where more positrons are coming from. If the positrons were coming from one or two nearby pulsars, you might expect a slight anisotropy, a bias toward the direction of those pulsars. AMS-2 does not see it. The arrival directions are consistent with random. That does not rule out pulsars. Positrons do not travel in straight lines through the galaxy. They are charged particles. The galactic magnetic field deflects them. They scatter off turbulence in the interstellar medium. By the time a positron emitted by a pulsar 1,000 light-years away reaches Earth, it has zigzagged through space so many times that its arrival direction no longer points back to the source. But the lack of anisotropy does mean that if pulsars are the source, there must be more than one, and they must be distributed in such a way that their combined signal looks uniform. Another problem is antiprotons. AMS-2 also measures antiprotons in cosmic rays. If the positron excess is coming from pulsars, you would not expect a corresponding antiproton excess because pulsars produce electron-positron pairs, not protons and antiprotons. Antiprotons are heavier and require much higher energies to produce. Most of the antiprotons detected by AMS should be secondary, created by cosmic ray protons colliding with interstellar gas. But some of the AMS data hints at a small excess of antiprotons at certain energies. Not as dramatic as the positron excess, but enough to make people wonder. If antiprotons are also elevated, that might suggest a different kind of source, something that produces both positrons and antiprotons. And that opens the door to more exotic possibilities. One possibility that keeps appearing in the literature is dark matter, specifically dark matter annihilation. If dark matter particles are their own antiparticles, which some theoretical models predict, then when two dark matter particles collide, they annihilate. The mass converts into energy. That energy produces particles. Depending on the mass and properties of the dark matter particle, the annihilation could produce positrons, antiprotons, gamma rays, neutrinos, all kinds of stuff. If dark matter is distributed in a halo around the Milky Way, and if it is annihilating at a rate high enough to be detectable, the annihilation products would diffuse through the galaxy and some of them would eventually reach Earth. AMS-2 would catch them. The positron and antiproton excesses could both be explained by dark matter annihilation if you tune the dark matter particle's mass and annihilation cross-section to match the data. This explanation is more speculative than the pulsar explanation. It requires dark matter to have properties we have not yet confirmed. Dark matter has never been directly detected. We only know it exists because of its gravitational effects on galaxies and galaxy clusters. We do not know what it is made of. We do not know if it interacts with normal matter through anything other than gravity, and we certainly do not know if it annihilates. The dark matter explanation for the positron excess is a hypothesis that solves one mystery by invoking another mystery. That does not make it wrong. It just makes it harder to test. A third, even stranger possibility emerged in 2024. A team analyzing AMS-2 data reported hints of antihelium nuclei in cosmic rays, not positrons, not antiprotons, antihelium. An antihelium nucleus is made of 2 antiprotons and 1 or 2 antineutrons, depending on the isotope. Antihelium-3 has 2 antiprotons and 1 antineutron. Antihelium-4 has 2 antiprotons and 2 antineutrons. These are much heavier and much rarer than individual antimatter particles. If antihelium is showing up in cosmic rays, it almost certainly cannot be secondary. The energies required to produce antihelium in a collision are enormous, and the cross-sections are tiny. The amount of antihelium you would expect from secondary production is effectively zero. So if AMS-2 is really seeing antihelium, and the jury is still out because the signals are at the edge of detectability and the statistics are weak, it means the antihelium is primary. It was created somewhere else and traveled here. The most exotic explanation, the one getting the most press, is that the antihelium is coming from antimatter regions of space. Pockets of the universe where the matter-antimatter asymmetry went the other way. Antimatter stars, antimatter gas clouds, maybe even antimatter galaxies far beyond the observable horizon. If such regions exist, and if they are interacting with normal matter at the boundaries, the collisions at those boundaries could produce all kinds of antimatter debris, including heavy antinuclei. Some of that debris could propagate through space and eventually reach our detectors. This is speculative, bordering on science fiction. No one has detected an antimatter galaxy. No one has seen the gamma-ray signature of large-scale matter-antimatter annihilation that would mark the boundary between a matter region and an antimatter region. The cosmic microwave background, the afterglow of the Big Bang, is extremely uniform. If the early universe had separated into matter and antimatter domains, you would expect to see imprints of that separation in the microwave background. We do not see them. So the antimatter domain hypothesis has to explain not just why antihelium is showing up in cosmic rays, but also why all the other evidence points to a matter-dominated universe with no large antimatter structures anywhere. The more conservative explanation for antihelium, if it is real, is that it is coming from a nearby astrophysical source we do not fully understand yet. Maybe a supernova remnant. Maybe a pulsar wind nebula. Maybe some kind of exotic stellar explosion that briefly created conditions hot and dense enough to forge antinuclei and eject them into space. This explanation does not require rewriting cosmology. It just requires finding the right kind of source and showing that it can produce the observed signal. Nobody has done that yet. The search is ongoing. Meanwhile, AMS-2 keeps collecting data. As of the most recent reports, it has recorded more than 400,000 positrons, the largest sample of cosmic ray antimatter ever collected. 100 times more data than all previous experiments combined. The positron fraction is now measured to within a few percent across the entire energy range AMS can observe. The antiproton fraction is also well measured, and the search for heavier antinuclei, antihelium and beyond continues. Every year the statistics improve, every year the uncertainties shrink, and every year the mystery of where all this antimatter is coming from gets a little bit clearer or a little bit stranger depending on what the new data shows. There is another source of antimatter that nobody expected, and it is much closer than pulsars or dark matter halos. Thunderstorms. In 2009, NASA's Fermi Gamma Ray Space Telescope detected bursts of gamma rays coming from thunderstorms on Earth. These bursts, called terrestrial gamma ray flashes, are extremely brief, lasting less than a millisecond, and extremely energetic. The gamma rays are produced by electrons accelerated to nearly the speed of light in the intense electric fields inside thunderclouds. When those electrons collide with air molecules or radiate gamma rays through a process called bremsstrahlung, some of those gamma rays are energetic enough to pair produce electron and positron. The positron is created in the atmosphere above the thunderstorm and gets swept upward by the electric field. Some of those positrons make it out of the atmosphere entirely and escape into space. Fermi detected them. Beams of antimatter shooting upward from the tops of thunderstorms. This was the first direct evidence that Earth itself is an antimatter factory. Not a large-scale factory. The total amount of antimatter produced by all thunderstorms worldwide is negligible compared to the cosmic ray flux. But it is real, it is measurable, and it proves that antimatter production is not limited to exotic astrophysical objects or expensive particle accelerators. It happens in the sky during storms. Somewhere on Earth, right now, a thunderstorm is producing positrons. Most of them annihilate within seconds against air molecules. A few escape and join the cosmic ray background, and nobody walking around below the storm has any idea it is happening. The rate at which antimatter hits Earth from all sources combined, cosmic rays plus occasional thunderstorm positrons, is about 100 particles per square meter per second. That sounds like a lot. It is not. You are roughly 1 square meter of surface area if you are standing up. So you are being hit by about 100 antimatter particles every second. Most of them are positrons with energies in the mega-electron-volt range. A positron at that energy passes through your body and annihilates somewhere inside you, most likely against an electron in one of your cells. The annihilation releases 2 gamma-ray photons, each with an energy of 511 kilo-electron-volts, the rest mass of an electron or positron. Those gamma rays deposit a tiny amount of energy in your tissue as they pass through. The dose is so small that it is completely irrelevant compared to the background radiation you get from natural sources like radon, cosmic rays in general, and trace radioactive elements in the ground. You have been soaking in antimatter your entire life, and it has done nothing to you. But the fact that it is happening at all is strange. The universe produces antimatter continuously, not in equal amounts with matter, not anymore, but enough that detectors in space can measure it, catalog it, and argue about where it came from. And the arguments are not resolved. Pulsars explain most of the positron excess, but not all of it. Dark matter could explain both positrons and antiprotons, but only if dark matter has properties we have not confirmed. Antihelium, if it is real, does not fit neatly into any existing model and might require new physics or new astrophysical sources we have not discovered yet. The data is piling up. The measurements are getting better, and the more precisely we measure cosmic antimatter, the more questions we generate. The universe is not supposed to have antimatter. It should have annihilated itself 14 billion years ago. But here we are, standing on a planet made of matter, being constantly pelted by antimatter particles from space, trying to figure out where they came from and why the balance broke in the first place. Every positron detected by AMS-2 is a clue. Every antiproton is a piece of the puzzle. And somewhere out there, in the wreckage of exploded stars, or the magnetospheres of pulsars, or the annihilation zones of dark matter halos, Or maybe even in pockets of antimatter that should not exist? The answer is waiting. We just have to keep looking up. You are being hit by antimatter particles right now, 100 per second, every second. Positrons mostly, a few antiprotons, all of them arriving at speeds close to light, products of cosmic ray collisions in the upper atmosphere or particle winds from distant pulsars. They pass through your body, annihilate against electrons in your cells, release tiny flashes of gamma radiation, and you feel nothing. The dose is negligible. The energy per particle is too small to matter. Your body absorbs more radiation from the potassium in a banana than it does from cosmic antimatter over the course of a year. This is background noise. This is normal. This is the universe gently reminding you that antimatter exists, and it is everywhere, and it is harmless as long as the amounts stay small. Now let's talk about what happens when the amounts stop being small. Imagine an object the size of a marble, 1 centimeter across, solid antimatter, not individual particles, not positrons drifting through space one at a time. A coherent lump of anti-atoms, bound together the way normal matter is bound together, dense and cold and stable. This object does not exist. As far as we know, nothing like it exists anywhere in the observable universe, but the laws of physics do not forbid it. Antimatter can clump. Antimatter can form molecules, solids, structures. The only reason it does not is that the universe is made of normal matter, and the moment antimatter touches normal matter, both vanish. So for this object to exist, it would have had to form in a region of space completely isolated from normal matter, an antimatter island in a matter ocean. We have never found such a place. We have looked. We see no evidence. But for the sake of this exercise, assume the marble exists. Assume it formed somewhere in the distant past, drifted through the void for millions or billions of years, and now, by the cruelest accident of orbital mechanics, it is on a collision course with Earth. The marble weighs about half a gram. Let's round it to 1 gram to keep the math simple. 1 gram of antimatter. It enters Earth's atmosphere at a typical meteor velocity, about 20 kilometers per second. Fast, but not relativistic. The moment it touches the first atoms of the upper atmosphere, the annihilation begins. 1 gram of antimatter meeting 1 gram of matter, 2 grams total, all of it converting to energy. E equals mc squared, 2 grams times 90 trillion. 1.8 times 10 to the 14th joules, 43 kilotons of TNT, 3 times Hiroshima, double Nagasaki, from a marble. The annihilation does not happen all at once. The marble is not going to survive long enough to reach the ground. As it plows through the atmosphere, the outer layers of anti-atoms collide with air molecules and annihilate continuously. Each annihilation releases a burst of gamma rays, pions, and other particles. The gamma rays deposit energy in the surrounding air, heating it to millions of degrees in a fraction of a second. The air ionizes, expands, turns into plasma. The marble is surrounded by a growing fireball, a sphere of superheated gas expanding outward faster than the speed of sound. The shock wave forms immediately, and the marble keeps falling, annihilating more atmosphere with every meter it descends, the fireball growing hotter and brighter until the entire object is consumed somewhere in the upper atmosphere, maybe 30 or 40 kilometers above the ground. What reaches the surface is not the marble. The marble is gone. What reaches the surface is the energy. 43 kilotons, delivered as a combination of thermal radiation, gamma rays, and a pressure wave propagating downward through the atmosphere at supersonic speed. The fireball, if you could see it from the ground before the shockwave arrived, would be brighter than the sun. The thermal pulse would ignite fires across a radius of several kilometers. The blast wave, when it hits, would flatten buildings, shatter windows, strip trees, and throw debris outward in every direction. The crater, if the annihilation were concentrated enough and occurred low enough in the atmosphere, would be modest, maybe a few dozen meters across. Nothing like the kilometer-wide scars left by large asteroid impacts. The energy is comparable, but the delivery mechanism is different. An asteroid transfers its kinetic energy into the ground through impact. An antimatter meteor transfers its energy into the atmosphere through annihilation. The result is more airburst than ground strike. For comparison, the Hiroshima bomb detonated about 600 meters above the city. The fireball never touched the ground. The explosion was an airburst by design, because airbursts maximize the area affected by the shockwave. The overpressure spreads outward in all directions with no terrain to block it. Everything within a 2-kilometer radius of the hypocenter was destroyed or heavily damaged. People standing outside within 1 kilometer were exposed to thermal radiation intense enough to cause third-degree burns instantly. The mushroom cloud rose more than 10 kilometers into the sky. That was 15 kilotons. Our antimatter marble is 43 kilotons. Scale everything up by a factor of 3. The radius of total destruction grows. The thermal pulse reaches farther. The fires spread wider. The shockwave flattens structures that might have survived a smaller blast. A small city hit by this event would cease to exist as a functioning entity within seconds. But let's be clear about what this is not. This is not an extinction event. This is not a dinosaur killer. 43 kilotons is a disaster for anything within a few kilometers of the detonation point. It is not a threat to the planet. The Chicxulub impactor, the asteroid that ended the Cretaceous period 66 million years ago, released energy equivalent to somewhere between 100 million and 1 billion megatons of TNT, depending on whose model you trust. That is roughly 100 trillion kilotons on the low end. Our marble releases 43 kilotons. The difference is not measurable in the same units. You would need more than 2 trillion antimatter marbles to match Chicxulub. At that point, you are not talking about a meteor. You are talking about an antimatter asteroid. And if something that large and that dense made of pure antimatter were falling toward Earth, we would have much bigger problems than calculating the yield. The real danger of an antimatter impact is not the raw energy, though that is bad enough. The real danger is the gamma radiation. When matter and antimatter annihilate, a significant fraction of the energy is released as gamma rays, high-energy photons. Each annihilation event between a proton and an antiproton produces pions that decay into gamma rays, with energies in the hundreds of mega-electron volts. A positron, annihilating with an electron, produces 2 gamma rays, each at 511 kilo-electron volts. The fireball from our marble would be pumping out gamma rays at a rate that makes a nuclear bomb look gentle. Gamma rays do not care about walls. They do not care about shelter. They pass through most materials with ease. Lead helps. Concrete helps. Distance helps more. But if you are anywhere near the blast, the radiation dose is going to be lethal. Not over years, not from fallout, immediately. The gamma flux from a 43 kiloton antimatter detonation at low altitude would deliver fatal doses of radiation to anyone within several kilometers of the event, even if they somehow survived the thermal pulse and the shockwave. There is another effect that most people do not think about. The annihilation produces a lot of neutrons. When pions decay, some of the decay products are neutrons. Those neutrons scatter through the atmosphere, collide with nitrogen and oxygen nuclei, and can induce secondary reactions that produce more radiation and more radioactive isotopes. The atmosphere itself becomes briefly radioactive, not in the long-term fallout sense like a fission bomb. The isotopes produced are short-lived, but in the immediate aftermath of the blast, the air downwind of the detonation would be carrying elevated levels of radiation for hours or days. This is not something you want to breathe. This is not something you want to be near. Now scale it up. Not a marble, a golf ball. 4 grams of antimatter. 170 kilotons, 10 times Hiroshima. Now you are approaching the yield of a modern tactical nuclear weapon. The destruction radius grows proportionally. Fires would ignite across tens of square kilometers. The blast wave would be strong enough to collapse reinforced concrete structures several kilometers from the detonation point. The gamma radiation would be lethal at distances where the thermal pulse is merely severe. A direct hit on a major city would kill hundreds of thousands of people instantly and injure millions more. The economic damage would be incalculable. The psychological impact would reshape the entire geopolitical landscape, and this is from 4 grams, the weight of a sugar cube. Keep scaling. A baseball. 145 grams, 6 megatons. Now you are in the range of the largest thermonuclear weapons ever deployed. The fireball would be kilometers wide. The thermal pulse would ignite everything flammable within 20 or 30 kilometers. The shock wave would flatten buildings across an area larger than most metropolitan regions. The mushroom cloud would punch into the stratosphere. A direct strike on a densely populated area would result in millions of casualties. This is city-ending scale. This is the kind of event that gets written into history books as a dividing line between before and after, and it comes from an object small enough to hold in your hand. At some point in this progression, the line between natural disaster and existential threat starts to blur. A kilogram of antimatter is 21 megatons. 5 kilograms is 105 megatons. Twice the yield of Tsar Bomba, the largest nuclear explosion in human history. 10 kilograms is 210 megatons. At these scales, the effects stop being local and start being regional. The thermal radiation is intense enough to ignite fires across hundreds of kilometers. The shock wave propagates across entire countries. The atmospheric disturbances could affect weather patterns. The gamma-ray burst, if it occurred at high altitude, could damage the ozone layer. The electromagnetic pulse from the ionized air could fry electronics across continents. You are no longer talking about a disaster. You are talking about a civilization-level disruption. The absurd part is that 10 kilograms is nothing. 10 kilograms of normal matter is a bag of flour, a small dumbbell, a house cat. We handle 10-kilogram objects every day without thinking about it, but 10 kilograms of antimatter is 210 megatons. It is more explosive power than the entire nuclear arsenal of most countries, and the energy density does not stop there. It scales linearly forever. 100 kilograms is 2.1 gigatons. 1,000 kilograms, a metric ton, is 21 gigatons. That is approaching the scale of the largest volcanic eruptions in recorded history. Krakatoa in 1883 released energy equivalent to about 200 megatons. Tambora in 1815, which caused the year without a summer and led to crop failures and famines across the northern hemisphere, released energy equivalent to about 800 megatons. A single metric ton of antimatter is 21,000 megatons, more than 25 times Tambora. And you could fit it in a cube 1 meter on a side. This is why the idea of an antimatter meteor is so deeply unsettling. Not because it is likely, it is not. The universe does not make bulk antimatter. Every observation we have ever made points to a cosmos that is matter-dominated at every scale. Galaxies are made of matter. Stars are made of matter. Planets are made of matter. The gas clouds between stars are made of matter. We see no evidence of antimatter structures anywhere. If antimatter galaxies existed, we would see the Annihilation signature where they met matter galaxies. We do not. If antimatter stars existed in our galaxy, we would see them. Spectroscopically, an antimatter star looks identical to a normal star. But dynamically, if an antimatter star's solar wind ever touched normal interstellar gas, the boundary would light up in gamma rays. We see no such signals. The interstellar medium is made of matter. The cosmic microwave background is consistent with a matter-dominated universe. The abundances of light elements, hydrogen, helium, lithium, match predictions from a universe where matter won and antimatter lost. So the chances of an antimatter meteor hitting Earth are not just low, they are effectively zero. For an antimatter object to exist long enough to travel through space and hit us, it would have to have formed in a region completely devoid of normal matter. That region would have to be large enough that the object could coalesce without encountering stray hydrogen atoms, cosmic dust, or any of the countless bits of matter floating through the galaxy. Then it would have to be ejected from that region, probably by some kind of explosion or collision, and sent on a trajectory that happens to intersect Earth. And it would have to survive the journey without hitting any interstellar matter along the way, which is difficult because space is not empty. The density of the interstellar medium is about 1 atom per cubic centimeter. That does not sound like much, but if you are traveling at 20 kilometers per second through a medium of normal matter and you are made of antimatter, you are annihilating atoms constantly. You are bleeding energy. You are shrinking. A small antimatter object, anything less than a few kilograms, would not survive the trip. It would annihilate itself against the interstellar medium long before it reached us. The only way an antimatter meteor could plausibly strike Earth is if it were large enough to have a protective crust. Imagine an antimatter asteroid several meters across. The outer layers encounter interstellar hydrogen and annihilate, releasing energy that heats the surrounding material. The heat causes the surface to sublimate or ionize, creating a thin shell of gas around the object. That shell acts as a buffer. Incoming hydrogen atoms annihilate against the gas instead of the solid core. The gas is constantly replenished by material boiling off the surface. The core survives. This is not impossible, but it requires the object to start out large, travel through a relatively low-density region of space, and arrive at Earth before it erodes completely. The odds are not good, and even if such an object existed, we would probably detect it. An antimatter asteroid plowing through the interstellar medium would be producing gamma rays continuously. It would glow, faintly but detectably. Gamma-ray observatories like Fermi would pick it up. We have seen no such objects, ever. So the scenario is implausible, bordering on impossible. But the reason it keeps coming up in thought experiments is because the physics is so stark. The energy density of antimatter is the highest energy density anything made of matter can have. You cannot do better than 100% conversion. Antimatter annihilation is the ceiling, and that ceiling is terrifyingly high. The fact that 1 gram equals 43 kilotons is not an approximation. It is not a model-dependent estimate. It is Einstein's equation applied with ruthless precision. The speed of light is 2.99792458 times 10 to the 8th meters per second. Square that and you get 8.9875517.9 times 10 to the 16th, Multiply by 2 grams, convert to kilograms, and you get 1.79751 times 10 to the 14th joules. 1 kiloton of TNT is 4.184 times 10 to the 12th joules. Divide, and you get 43 kilotons. The math does not care about your intuition. The math is exact. The reason conventional asteroid impacts are measured in megatons or gigatons is because asteroids are big and fast. The kinetic energy of a moving object is 1/2 mv squared, mass times velocity squared divided by 2. The Chelyabinsk meteor, the object that exploded over Russia in 2013, was about 20 meters across, weighed roughly 12,000 tons, and entered the atmosphere at about 19 kilometers per second. Plug those numbers in, and you get about 500 kilotons of kinetic energy. The explosion, which occurred at an altitude of 30 kilometers, shattered windows across 6 cities and injured more than 1,500 people. That was 500 kilotons from 12,000 tons of rock. Our 1-gram antimatter marble releases 43 kilotons from 2 grams total. The energy per unit mass is 10 million times higher. You do not need a 20-meter rock. You need a centimeter-wide marble. The difference is profound. This is also why antimatter weapons, if anyone ever figures out how to make them, would be strategically horrifying. A nuclear warhead weighs hundreds of kilograms. The fissile core is tens of kilograms. The rest is casing, explosives, electronics, triggering mechanisms. The entire device is large, heavy, difficult to transport, and extremely expensive to produce. An antimatter warhead would weigh grams. You could carry it in your pocket. You could fit dozens of them in a briefcase. Each one would yield megatons if you scaled up to kilogram quantities. The delivery problem becomes trivial. You do not need ICBMs. You do not need bombers. You just need a way to keep the antimatter from touching anything until you want it to. Which brings us back to the storage problem that has made all of this theoretical. We cannot store bulk antimatter. We can trap individual particles in magnetic bottles for hours or days. We can trap a few 100,000 antihydrogen atoms if we are very careful and very patient. But grams, kilograms, not even close. The gap between what we can do and what would be required to weaponize antimatter or to create a macroscopic object is measured in factors of trillions. CERN has produced a total of about 10 nanograms of antimatter over the entire history of its antimatter program, 10 billionths of a gram. 1 gram would require running the antimatter factory at full capacity for about 3 million years. By the time we reach that milestone, either we will have figured out much more efficient production methods, or we will have decided that making antimatter in bulk is a terrible idea and stopped trying. But the hypothetical matters because it clarifies what antimatter actually is. It is not magic. It is not science fiction. It is matter with opposite charge. The same particles, the same forces, the same quantum rules, just flipped. The danger comes entirely from the fact that we live in a matter-dominated universe. Bring antimatter into contact with that universe, and the reaction is instantaneous, total, and energetically obscene. 1 gram is 43 kilotons, always, no exceptions. The equation does not care whether the antimatter is in a marble, a bomb, a meteor, or a magnetic trap. The energy is there, locked into the mass, waiting. And the moment the antimatter meets matter, the lock breaks and the energy is released all at once in the purest expression of E equals mc squared that nature allows. If an antimatter meteor ever did strike Earth, the immediate concern would not be the crater. It would be the flash, the gamma-ray burst, the fireball expanding at thousands of meters per second. the shock wave flattening everything in its path. And then, in the hours and days after, the questions: where did it come from? How did it survive the journey? What does it mean that bulk antimatter exists somewhere in the universe? Because if one object made it here, there could be more. And if there are more, if antimatter structures are hiding in voids between galaxies or in regions of space we have not surveyed, then the map of the cosmos we have been building for the past century is missing something fundamental. A whole category of objects we assumed could not exist because the universe is matter-dominated and antimatter should have been erased billions of years ago. The fact that the scenario is implausible is not the same as impossible, and the fact that the energy release scales so brutally with mass means that even a small object, something you could hold in your hand, carries enough destructive potential to reshape a continent. The universe does not make such objects as far as we know, but the laws of physics allow them. And somewhere in that gap between what we observe and what the equations permit, there is a question that refuses to go away. If matter and antimatter are truly symmetric, if the only difference between them is charge, then why did matter win? What broke the balance? And could there be places far beyond our horizon where the balance went the other way? Those questions do not have answers yet. But the search for those answers has led physicists to probe the deepest symmetries in nature, to measure particles and antiparticles with a precision that borders on obsessive, and to look for the smallest hint that the rules are not as symmetric as they seem. Because if the symmetry is broken, even slightly, that breaking is the reason anything exists. One particle in a billion survived the annihilation. That particle became everything, and the process that allowed it to survive is written somewhere in the physics we have not fully uncovered yet. So we have established that antimatter is real, that it annihilates with devastating efficiency, that the universe should not exist because matter and antimatter should have destroyed each other completely, and that somehow, against all odds, matter won. One particle in a billion survived. Everything you see, everything you are, exists because of that tiny excess. The question that should be keeping physicists awake at night, and in many cases actually does, is not whether the asymmetry happened. The evidence for that is sitting right in front of you in the form of your continued existence. The question is how. What process, operating in the first moments after the Big Bang, could have created more matter than antimatter? What rule, buried somewhere in the laws of physics, allowed one side to win? The answer, if there is one, lives in a place most people have never heard of. A violation so subtle that it took decades to detect, and so weak that even after we found it, it does not come close to explaining what we observe. The violation has a name, CP violation, and it represents the only confirmed crack in the mirror symmetry between matter and antimatter that physics has ever found. It is not enough, not even close, but it is the only clue we have. And the search for where the rest of the asymmetry is hiding has become one of the defining quests of modern particle physics. Before we get to the violation, we need to talk about the conditions. Because the universe does not hand out matter-antimatter asymmetries for free. You cannot just wake up one morning in the early cosmos and decide that today is the day matter wins. There are rules. In 1967, Andrei Sakharov, the Soviet physicist who would later spend years under house arrest for criticizing his own government, published a paper outlining exactly what conditions would be necessary to generate a matter excess in a universe that started out symmetric. The paper was short, elegant, and it has guided every subsequent attempt to explain why we exist. Sakharov laid out 3 requirements. Miss even one, and the asymmetry does not happen. the universe resets to balance. Matter and antimatter annihilate in equal numbers, and you are left with nothing but radiation. The first condition is that there must be processes that violate baryon number conservation. Baryons are particles made of 3 quarks. Protons and neutrons are baryons. Baryon number is a quantum number that counts how many baryons you have minus how many antibaryons you have. In almost every reaction we have ever observed, baryon number is conserved. If you start with 2 baryons, you end with 2 baryons. They might change type. A proton might turn into a neutron, but the total count stays the same. Sakharov said that is not good enough. If you want to create more baryons than antibaryons, you need reactions that can change the baryon number. Processes that can create a net excess of baryons out of non-baryon particles. Without this, the universe stays balanced. Every baryon comes with an antibaryon, and they annihilate as soon as they meet. The second condition is that the laws of physics must violate something called C symmetry and CP symmetry. C stands for charge conjugation. It is the operation of flipping every particle to its antiparticle. An electron becomes a positron, a proton becomes an antiproton, quarks become antiquarks. If C symmetry held perfectly, the universe would not care whether you are made of matter or antimatter. The laws would be identical. Every reaction involving matter would have a corresponding reaction involving antimatter with the same rate, the same probability, the same outcome. P stands for parity. It is a spatial flip, like looking at the universe in a mirror. Left becomes right, clockwise becomes counterclockwise. For a long time, physicists assumed that even if C symmetry was violated, the combination of C and P together, called CP symmetry, would hold. Flip the charges and flip the mirror, and you should get back to a valid physical process. Sakharov said that is not enough either. CP symmetry has to be violated. The universe has to treat matter and antimatter slightly differently, not in obvious ways. Not in ways that make antimatter fall up instead of down, but in subtle ways buried in the rates of rare particle decays that allow certain reactions to favor matter over antimatter by a tiny margin. The third condition is that these processes must occur out of thermal equilibrium. This is the timing requirement. In the early universe, everything was extremely hot, and particles were constantly colliding, transforming, annihilating, being created from energy, and generally maintaining a kind of equilibrium where every process was balanced by its reverse. If the universe stayed in equilibrium, any matter excess you created would just annihilate back into balance. You need the expansion to be fast enough, the cooling to be rapid enough, that the universe falls out of equilibrium. Reactions that create more matter than antimatter happen, and before the reverse reactions can restore balance, the temperature drops too low for those reverse reactions to occur anymore. The asymmetry freezes in, it becomes permanent. All 3 conditions, baryon number violation, CP violation, departure from thermal equilibrium. Sakharov proved that you need all 3, and here is the uncomfortable part. The standard model of particle physics, the most successful theory in the history of science, the framework that has passed every experimental test for the past 50 years, contains all 3 ingredients. Baryon number violation exists in certain theoretical extensions of the standard model, though we have never directly observed it. CP violation exists. We have measured it. We know it is real. And the early universe definitely went through periods of rapid expansion where thermal equilibrium was broken. So, in principle, the standard model has everything it needs to generate the matter-antimatter asymmetry. In practice, it does not work. The CP violation we observe in the standard model is too weak, by a lot, by a factor of at least 10, and possibly much more, depending on whose calculation you trust. The standard model predicts an asymmetry of maybe 1 part in 10 billion. The observed asymmetry is 1 part in a billion, off by a factor of 10. That does not sound like much until you realize that in particle physics, being off by a factor of 10 means your theory is missing something big. Let's talk about where the CP violation actually shows up, because this is not abstract, this is measurable, detectable, real. The first hint came in 1964, long before Sakharov wrote his paper, when a team of physicists at Brookhaven National Laboratory was studying particles called neutral K-mesons. A K-meson, also called a kaon, is a particle made of a quark and an antiquark. The neutral kaon comes in 2 types, one called K0, which contains a down quark, and an anti-strange quark, and its antiparticle called K0 bar, which contains a strange quark and an anti-down quark. The interesting part is that these 2 particles can oscillate. The K0 can spontaneously transform into a K0 bar and back again. The particle becomes its own antiparticle and then flips back. This happens because of quantum mechanics and the weak nuclear force, and the oscillation is fast enough that if you create a beam of K0 particles, by the time they travel a few meters, a significant fraction of them will have turned into K0 bar. The Brookhaven team, led by James Cronin and Val Fitch, was studying how these kaons decay. Most of the time, neutral kaons decay into pions, lighter particles that come in charged and neutral varieties. The details of the decay depend on the quantum state of the kaon. Some kaons decay quickly into 2 pions, others decay more slowly into 3 pions. The team built a detector, set up a beam of kaons, and started measuring decay rates. What they found broke one of the fundamental symmetries everyone assumed was sacred. The kaons were decaying in ways that should not have been possible if CP symmetry held. Specifically, certain decay modes that should have been forbidden were happening at a tiny but measurable rate. The violation was small, about 2 parts in 1,000, but it was there, reproducible, undeniable. Cronin and Fitch published the result, and the physics community reacted with a mixture of shock and skepticism. CP symmetry was supposed to be untouchable. The idea that the universe could distinguish between matter and antimatter in its fundamental interactions was unsettling. If CP symmetry is broken, what does that mean for all the other symmetries we take for granted? What else is hiding in the equations that we assumed were perfectly balanced? It took decades to fully understand what was happening. The violation comes from the way quarks transform into each other through the weak force. Quarks come in 6 types, called flavors: up, down, charm, strange, top, and bottom. The weak force allows quarks to change flavor. An up quark can turn into a down quark by emitting a W boson. A charm quark can turn into a strange quark the same way. The rates at which these transformations happen are described by a mathematical object called the CKM matrix, named after Kabibo, Kobayashi, and Muskawa, the physicists who worked out the framework. The CKM matrix is a 3x3 grid of numbers that tells you the probability of one quark flavor turning into another. Most of the entries in the matrix are real numbers, but one of them, just one, is a complex number. It has an imaginary component, and that imaginary component is where the CP violation hides. Complex numbers in quantum mechanics represent phases. When you have a complex phase in a transition probability, it means that the process can interfere with itself in ways that depend on the direction of time. Running the process forward gives a slightly different probability than running it backward. And if you combine that with flipping all the charges, the CP operation, you get a difference between matter and antimatter. A reaction involving quarks will proceed at a slightly different rate than the corresponding reaction involving antiquarks. The difference is tiny. For most processes, it is completely negligible. But it is real, measurable, and it is the only source of CP violation in the Standard Model. Cronin and Fitch won the Nobel Prize in 1980 for their discovery. Kobayashi and Muskawa won the Nobel Prize in 2008 for the theoretical framework that explained it. And in the decades since, physicists have measured CP violation in other systems. B mesons, particles containing bottom quarks, also exhibit CP violation. The Bear experiment at Stanford and the Bell experiment in Japan spent years studying B meson decays and confirmed that the violations matched the predictions from the CKM matrix with exquisite precision. The agreement is so good that there is no room left for doubt. CP violation is real. It is part of the Standard Model. It is one of the ingredients Sakharov said you need to generate a matter-antimatter asymmetry. But here is the problem. The strength of the CP violation in the CKM matrix is proportional to something called the Yarlskog invariant, a particular combination of the matrix elements that measures how much CP violation you get overall. The value of the Yarlskog invariant is about 10 to the minus fifth. That is 0.00001. Tiny. When you plug that number into the equations for baryogenesis, the process of generating a matter excess in the early universe, you get an asymmetry that is far too small. The Standard Model predicts that for every 10 billion matter particles, there should be 10 billion minus 1 antimatter particles. The observed asymmetry is 1 in a billion, not 1 in 10 billion. The Standard Model is off by a factor of 10. Maybe more depending on the details of how the early universe cooled and what other processes were happening at the same time. This is called the baryogenesis problem. The Standard Model has all the ingredients Sakharov said you need, but when you run the numbers, the ingredients are not strong enough. The CP violation is too weak. The baryon number violation, which in the Standard Model only happens at extremely high energies through processes involving particles that have never been observed, is too slow. And the departure from thermal equilibrium during the electro-weak phase transition, a moment in the early universe when the weak force and electromagnetism separated into distinct forces, is not dramatic enough to freeze in a large asymmetry. The Standard Model can generate a tiny matter excess, but it cannot generate the matter excess we actually observe. Something else must have happened, some additional source of CP violation, some new interaction, some particle or force that we have not discovered yet. This is where the field splinters into competing ideas, because once you admit that the Standard Model is incomplete, the question becomes what is missing and where do you find it? The most popular class of solutions involves extending the Standard Model to include new particles and new interactions that provide stronger CP violation. These extensions go by names like supersymmetry, grand unified theories, extra dimensions, and a dozen other frameworks that all share the same basic goal. Add new physics at high energies, physics that we have not been able to access in particle accelerators yet, and use that new physics to generate the missing CP violation. The details vary wildly. Some models add new heavy particles that decay in CP-violating ways. Some add new forces that mix with the known forces in ways that enhance the asymmetry. Some add entire new sectors of particles that do not interact with normal matter except through gravity and CP-violating decays. One idea that has gained a lot of traction over the past few decades is called leptogenesis. The name comes from leptons, a class of particles that includes electrons, muons, torus, and their associated neutrinos. Leptogenesis proposes that the matter-antimatter asymmetry was not generated in the baryon sector at all. It was generated in the lepton sector and then converted into a baryon asymmetry through interactions that violate both lepton number and baryon number but conserve their difference. This sounds arcane, but the basic idea is simple. In the very early universe, heavy particles called right-handed neutrinos existed. These are hypothetical particles that have never been directly observed but are predicted by many extensions of the Standard Model. The right-handed neutrinos are extremely heavy, possibly trillions of times heavier than a proton, and they decay into lighter particles. Specifically, they decay into leptons and Higgs bosons. Here is the key part. If the right-handed neutrinos have CP-violating interactions, their decays will produce slightly more leptons than antileptons. Not a huge difference, just a tiny excess. But in the early universe, that excess can be amplified. Once you have more leptons than antileptons, processes involving the weak force and the Higgs field can convert some of that lepton asymmetry into a baryon asymmetry. The conversion is not one-to-one. The rates depend on the details of the interactions and the temperature of the universe at the time, but the end result is that you start with an excess of leptons and you end up with an excess of baryons. Matter wins. The universe survives. Leptogenesis is attractive because it ties the matter-antimatter asymmetry to another major unsolved problem in physics, the origin of neutrino masses. Neutrinos in the Standard Model are massless. But experiments over the past 20 years have shown that neutrinos do have mass, tiny masses, less than a millionth the mass of an electron, but non-zero. The simplest way to give neutrinos mass is to introduce right-handed neutrinos, and once you have right-handed neutrinos, leptogenesis becomes possible. You solve two problems with one mechanism: neutrino masses and matter-antimatter asymmetry. That is elegant. That is the kind of solution physicists dream about. Two mysteries, one explanation. The problem, as always, is that we have no direct evidence for right-handed neutrinos. They are too heavy to produce in current particle accelerators. If they exist, they would have decayed long ago in the early universe, and all we would see are their indirect effects. The lepton asymmetry they created, the baryon asymmetry that followed, the neutrino masses they generate through quantum effects. All of these are consistent with leptogenesis, but none of them prove it. You can explain the same observations with other mechanisms. The right-handed neutrinos might exist. They might not. We do not know. And until we find direct evidence, leptogenesis remains a hypothesis. A good hypothesis, a compelling hypothesis, but still just a hypothesis. There are other ideas. Some involve the strong force instead of the weak force. Quantum chromodynamics, the theory of quarks and gluons, has a parameter called theta that in principle could introduce CP violation. If theta were large, it would cause neutrons to have an electric dipole moment, a tiny imbalance in their charge distribution. Experiments have searched for the neutron electric dipole moment for decades and found nothing. The current upper limit is so small that it implies theta must be less than 1 part in a billion. That is unnaturally small. Why would a parameter that could be anything end up being almost exactly zero? This is called the strong CP problem, and it is one of the most frustrating puzzles in particle physics. The Standard Model allows theta to be large. Observations say it is tiny. Nobody knows why. Some physicists have proposed a new particle called the axion that dynamically sets theta to zero through a quantum field effect. If axions exist, they would solve the strong CP problem. They might also be the dark matter that holds galaxies together. Two problems, one particle. Again, elegant. Again, no direct evidence yet. Then there are the models that go beyond adding a few new particles and propose that the entire structure of the universe is different from what we thought. Some suggest that the asymmetry was not generated after the Big Bang, but was present from the beginning, built into the initial conditions. Maybe the universe started with slightly more matter than antimatter, for reasons we will never know, because those reasons are erased by cosmic inflation or hidden behind an event horizon we cannot see past. This explanation is deeply unsatisfying to most physicists because it does not explain anything. It just pushes the question back one step and declares that we are not allowed to ask further. Science is supposed to ask why. Declaring something an initial condition is giving up. But if every other explanation fails, if we exhaust every testable mechanism and still cannot account for the asymmetry, we might have to accept that the answer lies outside the part of the universe we can observe or reconstruct. The experimental side of this search is brutal. CP violation is hard to measure. It shows up in rare decays of unstable particles that only exist for fractions of a second before transforming into something else. You need huge numbers of events to see the tiny differences in decay rates between particles and antiparticles. The Barber and Bell experiments each recorded hundreds of millions of B-meson decays over the course of a decade. The LHCb experiment at CERN, which is specifically designed to study particles containing bottom quarks, has recorded billions of decays and is still finding new modes where CP violation shows up. Every new measurement refines the parameters in the CKM matrix. Every refinement tightens the constraints on how much CP violation the standard model allows. And every result so far has been consistent with the standard model. No surprises, no anomalies, no hint of the new physics that we know must be there. That consistency is both reassuring and frustrating. Reassuring because it means the standard model works exactly as well as we thought it did. Frustrating because it means the new physics is hiding. Either it is too weak to show up in current experiments, or it operates at energy scales we cannot reach yet, or it is buried in some corner of parameter space that we have not searched carefully enough. The LHCb experiment is now looking for CP violation in decays involving charm quarks, which are lighter than bottom quarks and decay through different mechanisms. The hope is that charm decays might be sensitive to new physics in ways that bottom decays are not. Early results show hints of CP violation in certain charm decay modes, but the statistics are still too weak to be certain. More data is needed, more years of running, more billions of decays recorded and analyzed. And while the experiments grind away at precision measurements, the theorists are building models. Hundreds of models, thousands of papers, each one proposing a different way to extend the standard model, a different particle, a different interaction, a different mechanism for generating the matter-antimatter asymmetry. Some models add one new particle, some add entire new families of particles. Some unify all the forces into a single framework at ultra-high energies and predict that baryon number violation happens through the decay of particles that weigh as much as a galaxy. Some propose that the asymmetry was generated during cosmic inflation, the brief period of exponential expansion in the first fractions of a second after the Big Bang, when quantum fluctuations were amplified into density variations that eventually became galaxies. Some suggest that the Higgs field, the field that gives particles mass, has additional components that we have not discovered yet, and those components couple to new particles in CP-violating ways. The landscape is vast, The possibilities are overwhelming. And the frustrating part is that most of these models make predictions that are almost impossible to test with current technology. They predict new particles that are too heavy to produce at the LHC. They predict interactions that are too rare to observe in a human lifetime of data collection. They predict effects that only show up at energies that existed in the universe for less than a billionth of a second after the Big Bang and have never existed since. You can write down the equations, you can solve them, you can show that they generate the right asymmetry, but if you cannot test them, they remain speculation. Educated speculation, mathematically rigorous speculation, but speculation nonetheless. There is one place where new sources of CP violation might show up in a measurable way, and it has become a major focus of experimental effort. Neutrino oscillations. Neutrinos come in three types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. As a neutrino travels through space, it can oscillate, transforming from one flavor to another and back again. The oscillations happen because the three neutrino flavors are quantum superpositions of three neutrino mass states. The mass states travel at slightly different speeds, and the interference between them causes the flavor to change. This is similar to how neutral kaons oscillate between particle and antiparticle. And just like kaons, neutrino oscillations can exhibit CP violation. If the CP violation in the neutrino sector is large, it would show up as a difference in the oscillation probabilities for neutrinos and antineutrinos. An electron neutrino oscillating to a muon neutrino might have a different probability than an electron antineutrino oscillating to a muon antineutrino. Several experiments are currently measuring this. The T2K experiment in Japan sends a beam of muon neutrinos from an accelerator on the east coast to a detector on the west coast through hundreds of kilometers of rock and measures how many of them have turned into electron neutrinos by the time they arrive. The NOVA experiment in the United States does the same thing with a longer baseline. Both experiments are also running with antineutrino beams and comparing the oscillation rates. Early results suggest there might be CP violation in the neutrino sector, but the uncertainties are still large. Confirming it will take more data, more years of running, and probably a new generation of experiments with better detectors and more intense neutrino beams. If neutrino CP violation is confirmed, and if it is large enough, it could be the missing piece. Not necessarily the whole explanation, because the CP violation you observe in neutrino oscillations today is not the same as the CP violation that would have operated in the early universe when right-handed neutrinos were decaying. But it would be a sign that the lepton sector is where the action is, that leptogenesis might be the right framework, that the matter-antimatter asymmetry is tied to the same new physics that gives neutrinos mass, and that would point the way forward. It would tell us where to look for the next clue. The broader point is that CP violation is not a solved problem. We have found one source of it in the standard model, and it is not enough. We need more. And the search for that more has driven experimental particle physics for decades. Every new collider, every new detector, every precision measurement of a rare decay is motivated in part by the hope that we will find the crack, the place where the standard model breaks. The hint of new particles, new forces, new interactions that can explain why anything exists. Because the alternative, that the standard model is complete and the asymmetry came from initial conditions we cannot probe or from physics at energy scales we will never reach, is the end of the road. It means the answer is out there, but we will never know it. And that is not an outcome anyone in the field is willing to accept without exhausting every other possibility first. So the experiments continue. LHCb keeps recording decays, T2K and NOVA keep measuring neutrino oscillations. Theorists keep building models. And somewhere in the data, in the tiny differences between matter and antimatter decay rates, in the quantum phases buried in mixing matrices, in the masses of neutrinos, and the couplings of hypothetical particles we have never seen, the answer is waiting. The universe is made of matter because something, some process, some interaction, some glitch in the symmetry allowed matter to win. We have found one glitch. It is not big enough, so we keep looking, and we will keep looking until we find the rest, or until we run out of places to look. Because the question is not optional. The question is, why are we here? And physics does not get to shrug and walk away from that one. So the standard model has CP violation, which is one of the 3 ingredients you need to explain why the universe is made of matter. But the violation is too weak. The numbers do not add up. The asymmetry we observe is 10 times larger than what the standard model predicts, maybe more, which means the explanation lives somewhere else. Somewhere outside the framework that has successfully described every particle interaction we have ever tested. The standard model is incomplete. That is not speculation, that is fact. And the search for what comes next, for the new physics that must exist beyond the edges of the known map, is where the real detective work begins. The most immediate place to look is neutrinos. Neutrinos are ghosts. They barely interact with anything. Trillions of them pass through your body every second, produced by the sun, by cosmic rays, by radioactive decay in the Earth's crust, and you feel nothing. A neutrino can travel through a light year of solid lead and have only a 50-50 chance of hitting anything. They are the least sociable particles in the standard model. For decades, physicists assumed neutrinos were massless. The standard model, as originally written, has no mechanism to give them mass. Electrons have mass because they interact with the Higgs field. Quarks have mass the same way. Neutrinos, as far as the theory was concerned, were supposed to glide through the universe at the speed of light forever, carrying no mass, feeling nothing. Then, in 1998, an experiment in Japan called Super Kamiokande detected something strange. The experiment sits in a mine about 1 kilometer underground, inside a cylindrical tank filled with 50,000 tons of ultra-pure water. The tank is lined with more than 11,000 photomultiplier tubes, detectors sensitive enough to catch the faint flash of light produced when a neutrino, on rare occasion, does interact with a water molecule. Super Kamiokande was built to study neutrinos produced in the atmosphere by cosmic ray collisions, muon neutrinos specifically. The team expected to see roughly equal numbers of muon neutrinos arriving from above, produced in the atmosphere directly overhead, and muon neutrinos arriving from below, produced in the atmosphere on the other side of the Earth. The neutrinos coming from below have to travel through the entire planet to reach the detector. But that should not matter. Neutrinos do not care about planets. They pass through the Earth like it is not even there. What Super Kamiokande found was that fewer muon neutrinos were arriving from below than from above. The deficit was clear, reproducible, and impossible to explain if neutrinos were massless. The only way the result made sense was if neutrinos were oscillating, transforming from one flavor to another as they traveled. A muon neutrino leaving the atmosphere on the far side of the Earth would travel thousands of kilometers through rock and magma, oscillate into a tau neutrino or an electron neutrino, and by the time it reached the detector, it would no longer register as a muon neutrino. The ones arriving from above, traveling only a few kilometers through the atmosphere, did not have time to oscillate. They arrived as muon neutrinos, and the detector saw them. The asymmetry in the arrival rates was direct evidence that neutrinos have mass, not much mass, less than a millionth the mass of an electron, but non-zero, and that was enough to break the standard model. If neutrinos have mass, the standard model needs an upgrade. The simplest upgrade is to add right-handed neutrinos. Neutrinos in the standard model are left-handed, a quantum property related to their spin and the direction they move. Left-handed particles interact with the weak force. Right-handed particles do not. If you add right-handed neutrinos to the theory, they can pair up with the left-handed neutrinos through the Higgs field the same way electrons and quarks get their masses. Problem solved. Neutrinos have mass. The math works. Everyone goes home. Except adding right-handed neutrinos does more than just give mass to the neutrinos we observe. It opens a door. Right-handed neutrinos do not interact with any of the known forces except gravity. They are completely sterile. And because they are sterile, there is no reason their masses have to be small. They could be light, they could be heavy. They could be anywhere on the mass scale, and the standard model would not care. The most natural expectation, based on the kinds of theories physicists like, is that right-handed neutrinos are extremely heavy. Not electron mass heavy, not even proton mass heavy. Something like 10 to the 15th giga-electron volts, which is 1 trillion times heavier than a proton. At those masses, the right-handed neutrinos would have existed only in the very early universe, when temperatures were high enough to create them. They would have decayed almost immediately into lighter particles. And those decays, if the right-handed neutrinos had CP-violating interactions, could have created a lepton asymmetry, more leptons than antileptons. That lepton excess, through a process involving the weak force and something called a sphaleron, gets partially converted into a baryon excess. More baryons than antibaryons. Matter wins, the universe survives. This is leptogenesis. The idea that the matter-antimatter asymmetry started in the lepton sector and got transferred to the baryon sector through interactions we understand reasonably well. The appeal of leptogenesis is that it ties two mysteries together. Why do neutrinos have mass? Because right-handed neutrinos exist. Why is the universe made of matter? Because right-handed neutrinos decayed in a CP-violating way. One mechanism, two explanations. Physicists love this kind of economy. It feels right. It feels like the kind of solution nature would use. The problem, as always, is proof. Right-handed neutrinos, if they exist and if they are as heavy as the theory suggests, cannot be created in any particle accelerator we will ever build. The Large Hadron Collider reaches energies of about 14 tera-electron volts, which sounds enormous until you realize that 10 to the 15th giga-electron volts is 1,000,000 times higher. We are not close. We will never be close unless someone invents a collider the size of the solar system. So the only evidence we have for right-handed neutrinos is indirect. Neutrino masses exist. Leptogenesis works in theory. The numbers can be tuned to match the observed matter-antimatter asymmetry if you choose the right masses and coupling strengths for the right-handed neutrinos. But tuning is not the same as predicting. If you have enough free parameters, you can fit any observation. That does not mean your model is right. It just means your model is flexible. The hope is that neutrino experiments will find something more direct. Not the right-handed neutrinos themselves, but clues about how neutrinos get their masses and whether there is CP violation in the neutrino sector. The T2K experiment in Japan and the NOVA experiment in the United States are both measuring neutrino oscillations with neutrino beams and antineutrino beams, looking for differences in how they oscillate. If the differences are large, it suggests that CP violation in the neutrino sector is significant. and significant CP violation in neutrinos would be consistent with leptogenesis, though not proof of it. Future experiments will push the measurements further. DUNE, the Deep Underground Neutrino Experiment, is under construction in South Dakota. When it comes online in the late 2020s, it will use the most intense neutrino beam ever built, fired from Fermilab in Illinois through 1,300 kilometers of rock to a massive detector sitting more than a kilometer underground in an old gold mine. DUNE will measure neutrino oscillations with a precision that no previous experiment has achieved. If CP violation is there, DUNE will see it. If it is not, or if it is too weak to matter, that will also be valuable information. Either way, we will know more than we do now. But neutrinos and leptogenesis are only one possibility. Another major contender for beyond the standard model physics is supersymmetry. Supersymmetry, usually abbreviated as SUSY, is the idea that every particle in the standard model has a partner particle with different spin. Electrons have selectrons, quarks have squarks, photons have photinos. The names are ridiculous, but the theory is serious. Supersymmetry solves several problems at once, which is why it has been popular among theorists for decades. It stabilizes the mass of the Higgs boson, which in the standard model is unnaturally sensitive to quantum corrections that should drive it to absurdly high values unless something cancels those corrections. SUSY provides the cancellation. It also predicts that the three forces of the standard model, electromagnetism, the weak force, and the strong force, unify at very high energies into a single force. Grand unification, which is another attractive idea that solves other problems, works much better if supersymmetry is real. And some of the lightest supersymmetric particles are stable and weakly interacting, which makes them excellent candidates for dark matter, the invisible mass that holds galaxies together and makes up about 85% of the matter in the universe. So SUSY solves the Higgs mass problem. It enables grand unification, and it gives you dark matter, 3 for the price of 1. In terms of theoretical elegance, SUSY is hard to beat. It also, in certain versions, provides additional sources of CP violation beyond what the standard model offers. The supersymmetric partners of quarks and leptons can have CP violating interactions that contribute to baryogenesis in ways the standard model cannot. If SUSY is real, and if the masses of the superpartners are in the right range, you can generate the matter-antimatter asymmetry without needing right-handed neutrinos or leptogenesis. SUSY becomes the explanation. The problem is that we have not found any superpartners. The LHC has been searching since it turned on in 2008. Physicists expected that if SUSY were the solution to the Higgs mass problem, the superpartners should be light enough to produce at the LHC. Early predictions put them within reach of the first few years of data collection. Selectrons and squarks and gluinos, the superpartners of gluons, should have shown up by now. They have not. Every search has come back empty. The LHC has explored masses up to a few tera-electron volts and seen nothing. No excess of events, no unexpected particles, no sign of supersymmetry. That does not prove SUSY is wrong. It just proves that if SUSY is real, the superpartners are heavier than we hoped. You can always push the masses higher. If the superpartners are heavy enough, they are out of reach of the LHC, and we will need a bigger collider to find them. But the higher you push the masses, the less natural the theory becomes. The whole point of SUSY was to solve the Higgs mass problem without fine-tuning. If the superpartners are too heavy, you need fine-tuning again. You are back where you started, just with a more complicated theory. Some physicists have started to lose faith in SUSY because of this. Others argue that we should keep looking. Absence of evidence is not evidence of absence. The superpartners could be just out of reach, one energy scale higher than the LHC can probe. The next collider, if it gets built, might find them, or it might not. The only way to know is to keep searching. If SUSY does exist, and if it provides the additional CP violation needed for baryogenesis, the process would have happened during a phase transition in the early universe. Probably the electro-weak phase transition, the moment when the Higgs field turned on and particles started acquiring mass. Before the phase transition, the universe was symmetric. Particles and antiparticles existed in equal numbers. During the phase transition, the Higgs field changed state and SUSY particles decayed or scattered in CP-violating ways. The interactions favored the production of matter over antimatter by a tiny margin. When the phase transition ended, the asymmetry was frozen in. Baryons outnumbered antibaryons by 1 part in a billion, and the rest annihilated. The universe cooled, expanded, and eventually formed stars and galaxies and everything we see. This scenario works on paper. It fits the timeline. It matches the observed asymmetry if you tune the parameters correctly. But without direct evidence for supersymmetry, it remains speculative. Plausible, but speculative. And plausibility is not the same as truth. Science does not advance on plausibility. It advances on data, and the data so far has been frustratingly silent. Grand unified theories, or GUTS, take a different approach. GUTS propose that at extremely high energies, much higher than anything the LHC can reach, the electromagnetic, weak and strong forces merge into a single unified force. The standard model treats these three forces as separate, each with its own coupling strength, its own gauge bosons, its own rules, but the coupling strengths change with energy. At low energies, electromagnetism is much stronger than the weak force. At high energies, the difference shrinks. If you extrapolate to high enough energies, somewhere around 10 to the 16th giga-electron volts, the coupling strengths converge, they meet, and if they meet exactly, that suggests the forces are not really separate. They are different aspects of one underlying force that breaks into three at lower energies, the way white light splits into colors passing through a prism. GUTS predict new particles and new interactions that do not exist in the standard model. One of the most striking predictions is proton decay. In the standard model, protons are stable. Baryon number is conserved in every interaction we have ever observed. A proton cannot decay into lighter particles because there is no lighter baryon for it to turn into. But in GUTS, baryon number is not strictly conserved. There are processes mediated by extremely heavy particles called X and Y bosons that can turn a proton into lighter particles like a positron and a neutral pion. The process is incredibly rare because the X and Y bosons are so heavy that they only exist as virtual particles in quantum fluctuations. But rare does not mean impossible. If GUTS are correct, protons should decay very slowly. The predicted lifetime is somewhere around 10 to the 34 years or longer, depending on the model. That is about 10 trillion times the current age of the universe. A long time, but not infinite. Experiments have been searching for proton decay for decades. Super Kamiokande, the same detector that discovered neutrino oscillations, is also watching for proton decay. If a proton inside the water tank decays, it will produce a flash of light as the decay products interact with the surrounding water. The signature is distinct, unmistakable. Super Kamiokande has been running for more than 20 years and has seen no convincing proton decays. The current lower limit on the proton lifetime is about 10 to the 34 years. That rules out some GUT models, but not all of them. The models with longer predicted lifetimes are still alive. Future experiments with even larger detectors might push the limits higher, or they might finally see a decay. Either outcome would be revolutionary. Finding proton decay would confirm grand unification and prove that baryon number is not conserved, which is one of the three Sakharov conditions. Not finding it after decades of looking would rule out an entire class of theories and force physicists to reconsider how the forces unify, if they unify at all. Guts also provide a natural setting for baryogenesis. If baryon number is violated at high energies through X and Y boson interactions, and if those interactions are CP violating, and if they occurred during a phase transition in the very early universe, you get all three Sakharov conditions in one framework: matter excess, CP violation, departure from equilibrium. The gut phase transition, which would have happened when the universe cooled below the unification energy, could have generated the asymmetry directly. The details depend on the specific gut model, and there are many competing models, but the broad outline works. Gut baryogenesis is one of the oldest ideas for solving the matter-antimatter problem, and it is still on the table because we have not found evidence against it. We also have not found evidence for it. Proton decay would be evidence for it. The discovery of gut-scale particles would be evidence for it. Measurements of the force coupling constants at high energies would be evidence for it. None of those have happened yet, so guts remain a possibility, supported by theoretical arguments and indirect hints, but not by direct observation. Then there is dark matter. Dark matter makes up the vast majority of the mass in the universe. We know it is there because galaxies rotate too fast to be held together by the gravity of their visible stars and gas. Galaxy clusters are more massive than the sum of their visible components. The cosmic microwave background has fluctuations that require more mass than we can see. All the evidence points to an invisible substance that interacts gravitationally but not electromagnetically. It does not emit light. It does not absorb light. It does not scatter light. It is dark. We call it dark matter. Nobody knows what dark matter is made of. The leading candidates are particles that were produced in the early universe and have survived to the present day without decaying. WIMPs, or weakly interacting massive particles, have been the favorite for years. WIMPs are hypothetical particles that interact through the weak force and gravity, but not through electromagnetism or the strong force. They would behave like neutrinos, but heavier, much heavier. If WIMPs exist, and if they were created in the right amounts in the early universe, they would naturally account for the observed dark matter density. The process that sets their abundance is called thermal freeze-out. In the hot early universe, WIMPs and anti-WIMPs were constantly being created and annihilating. As the universe cooled, the creation rate dropped and the annihilation rate dropped faster. Eventually, the density became so low that WIMPs stopped finding each other to annihilate. The population froze. Whatever was left at that moment is the dark matter we see today. If you run the numbers with plausible WIMP masses and interaction strengths, you get roughly the right dark matter abundance. It works. But WIMPs have not been found either. Dozens of experiments have been searching for dark matter particles colliding with normal matter in underground detectors. The idea is that dark matter is passing through the Earth constantly, and occasionally a dark matter particle will scatter off a nucleus in the detector, producing a tiny recoil that can be measured. The detectors are buried deep underground to shield them from cosmic rays and surrounded by layers of shielding to block radioactive contamination. They are the quietest, most sensitive instruments ever built, and after decades of searching, they have seen nothing. No clear dark matter signal. Just background noise. That does not prove WIMPs do not exist. It proves that if they exist, they interact even more weakly than we expected, or they are lighter than we thought, or heavier, or somehow different in ways we have not guessed yet. The search continues because the alternative, that dark matter is something we have not thought of at all, is unsettling. Some theories connect dark matter to the matter-antimatter asymmetry. If dark matter particles have some way of interacting with normal matter, even very weakly, they might have played a role in baryogenesis. One idea is that dark matter and normal matter are linked through a mechanism called asymmetric dark matter. In this scenario, the same process that generated more matter than antimatter also generated more dark matter particles than dark antimatter particles. The two asymmetries are related. The reason the universe has more baryons than antibaryons is the same reason it has more dark matter than dark antimatter. This would explain why the dark matter density and the normal matter density are roughly the same order of magnitude, which otherwise seems like a strange coincidence. If the two are generated by the same mechanism, the similarity is natural. Asymmetric dark matter is an elegant idea. It is also hard to test because dark matter barely interacts with anything, which makes it difficult to probe the details of how it was created. Future experiments will try. DOI, the neutrino experiment in South Dakota, is sensitive to more than just neutrinos. It can detect other weakly interacting particles if they happen to scatter in the detector. If dark matter particles are light enough and interact through some new force that couples to neutrinos or quarks, Dune might see them. Upgraded colliders, if they get built, will search for dark matter particles produced in high-energy collisions. Proposed experiments like the Future Circular Collider, a 100-kilometer ring that would dwarf the LHC, could reach energies high enough to produce sussy particles, gut-scale particles, or dark matter candidates that are out of reach today. The engineering challenges are enormous. The cost is staggering, measured in tens of billions of dollars. The political will to fund such a project is uncertain. But the physics case is strong. We know the standard model is incomplete. We know there is new physics out there. The question is whether we are willing to build the tools needed to find it. Another frontier is precision measurements. Not every discovery requires smashing particles together at record energies. Sometimes the new physics hides in tiny deviations from standard model predictions, effects so small that you need exquisite precision to see them. The anomalous magnetic moment of the muon is one example. The muon is a heavier cousin of the electron, and like the electron, it has a magnetic moment, a property related to its spin. The standard model predicts the muon's magnetic moment with extraordinary precision. But measurements at Fermilab and Brookhaven suggest that the actual value is slightly larger than the prediction. The difference is small, about 2 parts in a million, but it is persistent. If the discrepancy is real, it could be a sign of new particles contributing to the muon's magnetic moment through quantum loops. SUSY particles, dark matter particles, new force carriers, any of them could show up as a small correction to the magnetic moment. Or the discrepancy could be a statistical fluctuation or an error in the theoretical calculation. More data is needed. The muon G-2 experiment at Fermilab is collecting more data right now, refining the measurement, shrinking the uncertainties. Within a few years, we will know whether the anomaly is real or not. If it is real, it is a crack in the standard model, and cracks are where the light gets in. There are also experiments searching for electric dipole moments in particles. An electric dipole moment would indicate that a particle has a slight imbalance in its charge distribution, a separation between the center of positive charge and the center of negative charge. The Standard Model predicts that the electric dipole moment of the neutron and the electron should be incredibly small, far below current experimental sensitivity. But many beyond the Standard Model theories, including SISI and GUTS, predict larger dipole moments. If you can measure a non-zero electric dipole moment, you have found new physics, and if that new physics involves CP violation, it could be connected to the matter-antimatter asymmetry. Several experiments are pushing the sensitivity limits. The neutron electric dipole moment is currently constrained to less than about 10 to the minus 26 electron centimeters, which is an absurdly small number. Future experiments aim to improve that by another factor of 100 or more. Every incremental improvement narrows the space where new physics can hide. The timeline for answers is uncertain. Some of these experiments will report results in the next few years. Others will take a decade or more. Building Dune will take until the late 2020s. Upgrading the LHC or constructing a next-generation collider will take even longer. Proton decay searches will continue indefinitely, watching and waiting for an event that may never come. The dark matter detectors will keep running, refining their sensitivity, hoping that one day a particle will scatter in just the right way and light up their sensors. Science moves slowly. Discovery does not happen on schedule. But the work continues because the questions are too important to ignore. The matter-antimatter asymmetry is not just a curiosity. It is the reason the universe exists in a form that can support structure, chemistry, and eventually life. If the asymmetry had not occurred, or if it had been smaller, everything would have annihilated and we would not be here to ask why. The fact that we are here means something happened. Some process, some interaction, some piece of physics that we do not fully understand yet. The Standard Model gives us part of the answer, but not all of it. The rest is out there, hiding in the data we have not collected yet, in the particles we have not discovered yet, in the energies we have not reached yet. Finding it will require new experiments, new detectors, new colliders, and probably new ideas that we have not thought of yet. But the search is on, the tools are being built, the data is being collected. And somewhere in the numbers, in the tiny deviations from predictions, in the rare decays of unstable particles, in the oscillations of neutrinos, in the magnetic moments of muons, in the silence of dark matter detectors, the answer is waiting. We have spent this entire journey circling the same impossible fact. You exist. The atoms in your body exist. The planet beneath your feet exists. Every star in the night sky exists. And according to the rules written into the fundamental structure of reality, none of it should be here. The universe should have annihilated itself in the first second, erasing every particle, every possibility, every future that might have contained galaxies or chemistry or consciousness. And yet here we are, standing on a planet made of matter, breathing air made of matter, built from atoms that survived an extinction event so complete that only one particle in a billion made it through. This is not a metaphor. This is not philosophy dressed up in scientific language. This is the central mystery at the foundation of existence. The universe is made of matter because something, some process, some interaction, buried in the physics of the first moments after the Big Bang, broke the balance. Matter won. Antimatter lost. And every experiment we have ever run, every particle we have ever smashed together, every precision measurement we have ever made has brought us closer to understanding how that happened, but not close enough to answer it completely. We have found pieces, we have measured violations, we have built models that work on paper, and every single one of them falls short. The Standard Model has the ingredients, but not the strength. Leptogenesis has the mechanism, but not the proof. Supersymmetry solves multiple problems at once, but refuses to show itself. Grand unified theories predict new particles that decay so rarely we might never catch them. And dark matter, the substance that holds galaxies together, might be connected to the asymmetry or might have nothing to do with it at all. This is where we are. Decades into the search, billions of dollars invested in detectors and colliders and experiments scattered across the planet. Thousands of physicists staring at data, refining theories, proposing new tests. And the answer is still out there, hiding in the gaps between what we can measure and what we need to know. The matter-antimatter asymmetry is not just an unsolved problem. It is the unsolved problem, the one that determines whether the universe becomes a lifeless bath of radiation or a cosmos filled with stars and planets, and the possibility of something looking up at the sky and asking why. The scale of the mystery is clarified when you remember what antimatter actually does. 1 gram of antimatter meeting 1 gram of matter releases 43 kilotons of energy. 3 times Hiroshima, from 2 grams of material. That energy is not stored in chemical bonds or nuclear configurations. It is the mass itself converting directly into light and heat and gamma rays according to Einstein's equation with perfect ruthless efficiency. 100% conversion. The ceiling, you cannot do better. And the reason that conversion happens at all is because matter and antimatter are opposites. Same particles, opposite charge. Touch them together and they erase each other completely. In the first fraction of a second after the Big Bang, the entire universe was filled with particles and antiparticles created in equal amounts from pure energy. For every quark, an antiquark. For every electron, a positron. The universe was symmetric, balanced, and if it had stayed that way, everything would have annihilated. The energy would have spread thin and cold across expanding space, and that would have been the end of the story. No atoms, no chemistry, no complexity of any kind. Just photons, neutrinos, and an ever-dimming glow. But something tipped the scale. 1 extra particle of matter for every billion particles of antimatter. That is the margin. That is the razor's edge. A billion pairs annihilated. 1 particle was left over, and that leftover particle, multiplied across the entire volume of the early universe, became everything. You are made of the excess. So is everyone you have ever met. So is the ground beneath your feet, and the sky above your head, and every galaxy stretching to the horizon of the observable universe. All of it is debris from an asymmetry so slight that if you had been counting particles in the early cosmos, you would have needed to reach 1 billion just to find 1 extra on the matter side. The fact that we know this much is extraordinary. The fact that we still do not know why it happened is frustrating. And the fact that the answer has eluded us for more than 50 years, despite the most sophisticated experiments ever built, tells you something about how deeply the explanation is buried. The process that created the asymmetry operated under conditions that no longer exist. Energies that have not been present in the universe since the first microseconds. Temperatures measured in trillions of degrees. Particle interactions involving forces and particles we may never recreate in a laboratory. We are trying to reverse engineer an event that happened 14 billion years ago, using only the faintest clues left behind in the behavior of particles today. CERN is at the center of this search. The European Organization for Nuclear Research, sitting on the border between France and Switzerland, operating the most powerful particle accelerators on Earth. The Large Hadron Collider smashes protons together at energies high enough to recreate conditions that existed fractions of a second after the Big Bang. Every collision produces a spray of particles. Some of those particles are antimatter. positrons, antiprotons, heavier antimatter fragments that exist for microseconds before decaying into lighter pieces. The detectors surrounding the collision points record everything, every track, every energy deposit, every decay signature. And buried in those billions of events, physicists are searching for the violations. The tiny differences between how particles behave and how antiparticles behave that might explain why matter won. The LHCb experiment, one of several large detectors at CERN, is specifically designed to study particles containing bottom quarks, B mesons, short-lived particles that decay in dozens of different ways. Some of those decays exhibit CP violation, the asymmetry between matter and antimatter that Sakharov identified as one of the necessary ingredients for baryogenesis. The LHCb collaboration has recorded billions of B meson decays and measured the CP violation with extraordinary precision. Every measurement refines the parameters in the CKM matrix, the mathematical structure that describes how quarks transform into each other through the weak force. And every result so far has been consistent with the standard model. No surprises, no anomalies. No hint of the new physics that must be there. That consistency is both a triumph and a problem. A triumph because it shows the standard model works exactly as well as we thought. A problem because the CP violation in the standard model is too weak to explain the observed matter-antimatter asymmetry. The numbers do not add up. We are off by a factor of 10, maybe more, which means the explanation lives somewhere else, somewhere beyond the edges of the known map. The standard model is incomplete, and the search for what comes next is where the real detective work is happening. CERN's antimatter program is also trapping antimatter atoms and studying them directly. The Alpha experiment creates antihydrogen, the simplest antimatter atom, and holds it in magnetic traps for hours or days. The goal is to measure whether antihydrogen behaves exactly like hydrogen, same energy levels, same response to light, same gravitational behavior. If there is any difference, even a tiny one, it would mean the symmetry between matter and antimatter is not as perfect as we thought, and that difference might point the way toward the missing physics. So far, every test has shown that antihydrogen is identical to hydrogen within experimental precision. The symmetry holds, which deepens the mystery. If matter and antimatter are truly identical except for charge, why did one win and the other lose? CERN is not the only place searching for answers. Neutrino experiments scattered around the world are measuring oscillations, the quantum process where neutrinos transform from one flavor to another as they travel. If neutrinos exhibit CP violation, and early results suggest they might, it would support the idea that the matter-antimatter asymmetry was generated in the lepton sector through a mechanism called leptogenesis. The T2K experiment in Japan sends a beam of neutrinos across the country and measures how many have changed flavor by the time they reach the detector on the far coast. NOVA in the United States does the same thing with a longer baseline. DUNE, the next-generation experiment under construction in South Dakota, will measure neutrino oscillations with unprecedented precision when it comes online in the late 2020s. If CP violation in neutrinos is large enough to matter, DUNE will see it. And if it does, that will be the strongest evidence yet that leptogenesis is the right framework. Meanwhile, experiments searching for dark matter continue to refine their sensitivity. Dark matter makes up most of the mass in the universe, and we have no idea what it is made of. If dark matter particles interact with normal matter, even very weakly, they might be connected to the matter-antimatter asymmetry through a mechanism called asymmetric dark matter. The same process that created more matter than antimatter might have created more dark matter than dark antimatter. That would explain why the dark matter density and the normal matter density are roughly the same order of magnitude, which otherwise seems like a strange coincidence. Testing this idea requires detecting dark matter particles directly, which nobody has managed to do yet, despite decades of trying. But the detectors are getting better, the backgrounds are being reduced, the sensitivity is improving. And if dark matter finally shows itself, the discovery will reshape the entire conversation about where the asymmetry came from. There are also searches for particles that should not exist if the standard model is complete. Proton decay is one of the most striking predictions of grand unified theories. If the electromagnetic, weak and strong forces merge at very high energies, baryon number is not strictly conserved, and protons can decay into lighter particles. The process is incredibly rare. The predicted lifetime is longer than 10 to the 34 years, which is a trillion times the current age of the universe. But rare does not mean impossible. Super Kamiokande in Japan has been watching for proton decay since the mid-1990s. The detector sits in a mine about a kilometer underground, inside a tank filled with 50,000 tons of ultra-pure water. If a proton decays, it will produce a flash of light that the surrounding photomultiplier tubes will catch. So far, no convincing decays have been observed. The lower limit on the proton lifetime is now above 10 to the 34 years. That rules out some grand unified theories, but not all of them. Future experiments with even larger detectors will push the limit higher, or they might finally see a decay. Either outcome would be revolutionary. Precision measurements are another frontier. The anomalous magnetic moment of the muon, the electric dipole moments of the neutron and the electron, the masses and mixing angles of neutrinos, all of these quantities are predicted by the standard model with extraordinary precision. And in several cases, the measurements hint at small discrepancies. The muon's magnetic moment appears to be slightly larger than the standard model predicts. The difference is only 2 parts in a million, but it is persistent. If the discrepancy is real, it could be a sign of new particles contributing to the muon's properties through quantum loops. Fuzzy particles, dark matter particles, new force carriers, any of them could show up as a tiny correction. The muon G-2 experiment at Fermilab is collecting more data right now. Within a few years, we will know whether the anomaly is real or a statistical fluctuation. If it is real, it is a crack in the standard model, and cracks are where the light gets in. The timeline for answers is uncertain. Some experiments will report results in the next few years. Others will take a decade or more. Building new colliders, if they get funded, will take even longer. The proposed Future Circular Collider, a 100-kilometer ring that would dwarf the LHC, could reach energies high enough to produce particles that are completely out of reach today. Supersymmetric partners, if they exist, grand unified theory particles, dark matter candidates, new sources of CP violation. All of it could be waiting just one energy scale higher than we have reached so far. But the engineering challenges are enormous. The cost is staggering, measured in tens of billions of dollars, and the political will to fund such a project is uncertain. Science moves slowly. Discovery does not happen on schedule. But the work continues because the questions are too important to ignore. And here is the part that should make you uncomfortable. We might not solve this, not in our lifetimes, not in the next century. The answer might be hiding at energy scales we will never reach with technology we will never build. The right-handed neutrinos, if they exist and if they are responsible for leptogenesis, could weigh 1 trillion times more than a proton. We cannot create particles that heavy. The only place they existed was in the first microseconds after the Big Bang. If the matter-antimatter asymmetry was generated during cosmic inflation, the brief period of exponential expansion in the first fraction of a second, the process occurred under conditions so extreme that we might never recreate them or probe them directly. The evidence is gone, erased by 14 billion years of expansion and cooling. All we have are the consequences. A universe made of matter and a hole in our theory where the explanation should be. That is the worst-case scenario. The answer exists, but it is out of reach forever. We are left with models that work on paper, parameters that can be tuned to match observations, and no way to test whether any of it is actually true. That outcome would not be unprecedented. Cosmology is filled with questions we may never answer definitively because the events happened once, in conditions we cannot recreate, and the direct evidence is lost. But it would be deeply unsatisfying. The matter-antimatter asymmetry is not some obscure detail buried in the footnotes of particle physics. It is the reason anything exists. The universe should have annihilated itself. It did not. And if we cannot figure out why, we are missing something fundamental about how reality works. The best-case scenario is that the new physics is just out of reach, one energy scale higher, one generation of experiments away. Dune finds large CP violation in neutrinos and confirms that leptogenesis is the right framework. Or the next collider discovers supersymmetry, and the superpartners provide the additional CP violation needed to generate the asymmetry. Or dark matter is detected and its properties reveal a connection to the matter excess. Or proton decay is observed and grand unification becomes an experimental fact rather than a theoretical hope. Any one of those discoveries would crack the mystery wide open. It would tell us where to look next. It would give us the tools to build a complete theory of how the universe survived its own birth. And that is the profound philosophical implication lurking beneath all of this. The matter-antimatter asymmetry is not just a physics problem. It is an existence problem. If the asymmetry had not occurred, nothing would exist. No stars to forge heavy elements. No planets to host chemistry. No chemistry to build life. The fact that you are here, the fact that you are reading these words, the fact that anything is here at all, depends entirely on a process we do not understand, operating under conditions we cannot recreate, producing an imbalance we cannot fully explain. One particle in a billion survived. That particle became everything. And the mechanism that allowed it to survive is written somewhere in the laws of physics we have not uncovered yet. This is why the search matters. This is why thousands of physicists are dedicating their careers to building detectors, analyzing data, refining theories, and proposing new experiments. This is why governments spend billions of dollars on particle accelerators and underground laboratories and satellite observatories. Because the question is not optional. The question is, why are we here? And physics does not get to shrug and declare the answer unknowable without exhausting every possibility first. The universe is the greatest detective story ever told. The crime scene is 14 billion years old. The evidence has been scattered across expanding space, diluted by cosmic evolution, buried under layers of complexity that have accumulated over eons. The suspects are particles and forces that might not exist anymore, interactions that operated at energies we may never reach, symmetries that were broken in the first moments and have stayed broken ever since. The detectives are us. Armed with particle accelerators, magnetic traps, neutrino beams, dark matter detectors, and the mathematical frameworks that describe how reality behaves at its deepest levels, and the case is still open. Every new measurement is a clue. Every precision test narrows the possibilities. Every discovery, Even a negative result tells us something about where the answer is not hiding. The standard model works too well to be completely wrong, but not well enough to be the whole story. CP violation exists, but it is too weak. Neutrinos have mass, but we do not know why. Dark matter is everywhere, but we cannot see it. Supersymmetry solves multiple problems at once, but refuses to appear. Grand unified theories predict proton decay, but the proton has not decayed. The universe is taunting us, giving us just enough information to know that the answer exists, while keeping the final piece out of reach. But we are closer than we have ever been. The tools are better, the measurements are more precise, the theories are more refined, and the experiments planned for the next few decades will probe deeper into the unknown than anything that came before. Dune will measure neutrino oscillations with a precision that could finally confirm CP violation in the lepton sector. The next generation of dark matter detectors will search for interactions so rare that current experiments cannot see them. Upgraded colliders, if they get built, will reach energies that might produce the superpartners or the grand unified theory particles that have been hiding just beyond our reach. Precision measurements of the muon magnetic moment, the neutron electric dipole moment, and the properties of the Higgs boson will test the standard model in ways that might reveal the cracks where new physics is leaking through. And somewhere in all of that data, in the billions of particle collisions, in the millions of neutrino interactions, in the years of watching for dark matter particles that might never come, the answer is waiting. The process that broke the symmetry. The interaction that favored matter over antimatter by 1 part in a billion. The reason the universe survived instead of erasing itself in a flash of gamma rays. The explanation for why you are here instead of nothing. That answer, when we find it, will not just solve a physics problem. It will complete the story of how the universe became capable of supporting structure, chemistry, and eventually consciousness. It will tell us what happened in the first moments after the Big Bang that allowed the future to exist. It will connect the most abstract mathematics of particle physics to the most tangible fact of existence, that we are here to ask the question in the first place. And it will force us to confront the staggering improbability of our own survival. 1 particle in a billion made it through. Everything you are, everything you know, everything that has ever mattered to anyone exists because of that 1 particle. The universe is not supposed to look like this. It is supposed to be empty, silent, a thin haze of radiation cooling toward absolute zero, with no stars, no planets, no observers to wonder why it is empty. But it is not empty. It is filled with galaxies, trillions of them, each containing billions of stars, each star surrounded by the possibility of planets. Each planet, if conditions are right, capable of hosting the chemistry that leads to life. And all of it, every atom, every structure, every moment of complexity traces back to an asymmetry so small that it almost did not matter. Almost, but not quite. The universe teetered on the edge of annihilation, and then, for reasons we are still trying to understand, it chose existence. That choice, if you can call it a choice, is written in the laws of physics. Somewhere in the equations, in the coupling constants, in the mixing angles, in the phase shifts buried in the quantum mechanics of particle interactions, there is a number, a parameter, a term that does not quite cancel the way perfect symmetry would require. And that term, that tiny deviation from balance, is the reason everything exists. Finding it is not just an academic exercise. It is not just another measurement to add to the pile. It is the answer to the oldest question humans have ever asked. Why is there something instead of nothing? We do not have that answer yet, but we are looking. And we will keep looking until we find it, or until we run out of places to look. Because the alternative, Accepting that the universe exists for no reason we can ever discover is not an option. Not for science, not for a species that has spent millennia staring at the stars and demanding explanations. The matter-antimatter asymmetry is the greatest mystery in physics, the biggest unsolved problem in cosmology, the final piece of the puzzle that explains how the universe survived its own birth. And the search for that piece is the universe's greatest detective story. The case is open, the investigation continues, and the answer, when it comes, will change everything. So here is what we know. Antimatter exists. It annihilates with perfect efficiency. 1 gram equals 43 kilotons. The equation does not care about your intuition. And 14 billion years ago, the universe filled itself with equal amounts of matter and antimatter, brought them together, and should have erased everything in the largest explosion reality has ever known. But it did not. 1 particle in a billion survived. That particle became you, became everything. The stars, the planets, the periodic table, the entire architecture of complexity that allows anything interesting to happen. All of it exists because something broke the balance. Something tipped the scale by the smallest imaginable margin and then walked away without leaving a clear signature. We have been chasing that something for more than 50 years. We have built particle accelerators the size of cities. We have trapped individual antimatter atoms in magnetic bottles and held them long enough to ask if they fall the same way normal atoms fall. We have measured violations so subtle that detecting them required recording billions of particle decays and searching for differences of 2 parts in 1,000. We have found pieces. We have measured the violations. We have written down the equations. And every single piece we have found is not enough. The standard model has the ingredients but not the strength. The CP violation is real but too weak. The mechanisms work on paper, but the parameters have to be tuned. We are close, but close is not the same as done. The answer is out there, hiding in the next generation of experiments, or the one after that, or buried at energy scales we will never reach. Either way, the fact remains. You should not exist. The universe